Hello, everyone. Welcome to the December 2024 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. In the aftermath of the recent presidential election here in 2024, I was struck by a report on CNN where they sent a reporter to a UFC fight, I think it was, outside Madison Square Garden, and the reporter interviewed some audience members who had voted for Donald Trump. Not so much about why they voted for Donald Trump, but about where they got their information. What was their source of political information, opinions, etc. Now, given that it's a UFC fight, you'll be unsurprised to learn that many of them said Joe Rogan, because Joe Rogan, of course, is a UFC commentator as well as an extremely popular podcaster. But it was broader than that. It wasn't just Joe Rogan. And of course, this is a highly non-scientific, non-representative sample, but there were a lot of people saying that where they got their information from was basically some combination of podcasts, Reddit, TikTok, message boards, things like that. Not, let us say, the traditional media landscape. And I think it's broader than politics. I think this is a very, very true thing. Certainly, I'm not the first person to point this out. This is not an original idea, but kids these days, the information landscape is changing quite dramatically. I've noticed as a professor that a lot of my students, whether in physics or philosophy, got their start by listening to podcasts. I've had philosophy students who were still motivated by the questions they heard on Sam Harris's podcast, or physics students who were originally excited by Neil deGrasse Tyson's podcast back in the day, or whatever. This is not necessarily a bad thing. It's a thing, right? It's a feature of the modern landscape that we have splintered our information sources, and that's for better or for worse. That allows for much better, more focused, more precisely laser-targeted information sources. And it also allows for a bunch of nonsense to sneak through, and with very little overall quality control, precisely because of that splintering. All of which is to say, I'm just to let you know, thinking out loud kind of thing, I do occasionally wonder whether I'm doing the right thing here with the Mindscape podcast. Even though our audience is much bigger than I thought it ever would be, we're still a niche audience here, right? These are high-level intellectual conversations with people who are experts in their fields, many of whom have PhDs, talking specifically about usually some issue of substance, rather than sort of general purpose punditry, etc. And I think it's been super successful in many ways, but still one should ask, is it the right thing to do? Am I, using my powers for as much good as I can? Would it be better if I had a podcast that, tried to be a good role model for young men, or tried to be an accurate source of cultural, political, artistic information that was of a more broad kind than the specific kind of PhDs that I talked to? All of which is to say, I think the answer is no. I think the answer is that there's not any obvious way that I could be doing it better, more productively. I mean, as I often say, the idea behind my podcast is not that it is the best possible podcast I could be doing. It has to be something that keeps me interested, and a very large motivation for me is learning new things. So a big, big, big part of why Mindscape is the way it is because it's the way that I think that I can most productively learn new things and put them to use and talk to interesting people in ways that keep me motivated, rather than trying to be some kind of general purpose pundit or expositor, etc. But also I do think that of the things I am good at, I am better at talking to people like that than I would be at sort of general purpose pontificating. So I can do that here in the AMAs a little bit, some general purpose pontificating, but it's certainly not the point of the Mindscape podcast. And, I'm happy to get opinions otherwise. I have don't worry. Do not panic. I have no plans to dramatically change the format of Mindscape or anything like that. But again, it's always important to think through the possibilities. I think that given what I can do and what I'm good at doing, this is more or less the best thing that I should be doing, and I'm happy to keep doing it for a while anyway, not for 100 years in the future, but for some number of years. And but I do wonder. I do wonder if there's something better to do for the world, if there's some way to have a bigger impact. Again, probably not that I can see, but it's something to keep in mind. Which is to say, all of us should be thinking about, given what we can do for the world and in the world, how do we best optimize over what's good for us and what's good for the world? I think I'm going to say somewhere in this podcast that when I myself was in college and growing up and whatever, I was lucky enough to stumble upon something I wanted to do for a living quite early on in terms of becoming a physicist, et cetera. But I do think that it was a mistake that I didn't spend more time thinking through the possibilities along the way. I was pretty dedicated to what I wanted to do, and I kind of knew what to do next to make it happen. And so that's what I did. But one should always take a breath, step back, and wonder whether one is doing the right thing. The end of the year is a good time to be doing these kinds of things. So thus, here I am speaking out loud about it, which is to remind you, there is no AMA next month because holiday break time. So the next time there'll be an Ask Me Anything episode will be the beginning of February 2025. Occasional reminder, the AMAs are brought to you by the wonderful good spirit of our Patreon supporters. You could be a Patreon supporter if you wanted to. Go to patreon.com/Sean M. Carroll and you can support Mindscape with a couple of dollars a month or something. It should be dollars per month now, not dollars per episode. Yeah, so I got to figure out how to make that work because Patreon is changing its system. And then if you're a Patreon supporter, you get to have ad-free versions of the podcast, and you get to be the people asking questions every month. And every once in your lifetime, you even get to ask a priority question. Plus, you get to talk to other people who are Patreon supporters. When people, for people who are Patreon supporters and ask the AMA questions, you know that very often others will chime in to try to answer those questions. I don't read those answers out loud, but they're often very, very useful. Sometimes sufficiently useful, I don't even have to answer the question in the AMA itself. But if it's an interesting question that I think I have something to say about, then I will definitely try to answer it here in the AMAs. Thanks to everyone for being a listener of the Mindscape podcast. It's an amazing audience that we have. And have a great year planned for you in 2025. So let's see how that goes. Let's go. Brian asks a priority question. Remember, the priority questions are ones that Patreon supporters are allowed to ask once in their lives, so you better make it a good one, and then I'll do my best to try to answer. How does real patterns' ontology account for the existence of real boundaries or borders between different patterns or objects, especially if one denies... I think it maybe means divides. I think it was a typo, especially if one divides the world just in giant blobs, but also takes the stance that the world isn't divided up until humans carve into standalone entities or kinds. I think this is exactly the point of Dan Dennett's Real Patterns paper, which I encourage people to read. Even though he was a professional philosopher, sometimes writing professional philosophy papers, he was always very readable and fun. And the point is that there are some real patterns and not others, right? Like take the existence of a table or a chair. These are always some of my favorite examples of emergent phenomena, which most people think exist, right? Even though they're nowhere to be found in the core theory, the standard model of particle physics, anything like that. The point of taking a certain collection of atoms and bundling them together as a table, and likewise for chairs and likewise for people and carpets and other things that you see around you, is that those are the categories that give you information about the macroscopic world, that specifying what those categories are doing, where is the table, how many chairs are there, okay? You instantly know something about the world that allows the future to be predicted. If there are a certain number of chairs, I will have enough chairs for the number of people that I invited to the party, right? And Dennett explicitly, I forget his exact examples, but he contrasts this with, taking half of the atoms inside the chair and another bunch of atoms inside a cloud somewhere, right? That particular group of atoms doesn't give you any handle on anything. Knowing that the center of mass of that group of atoms doesn't really help you very much at all. And the point is, at a very mathematical level, this is real. The word real and real patterns matters. There are certain ways to group the world into things that give you independent, autonomous ability to predict what will happen next without knowing all of the microscopic details. This has nothing to do with humans carving it up. The existence of the Earth's center of mass and the ability to the fact that knowing the Earth's center of mass and the sun's center of mass and likewise their momenta is sufficient to predict what will happen to the Earth orbiting around the sun is completely objective. It has nothing to do with human beings. It's not just a convenience for human beings. That's what the word real means here. There are other carving ups that would not have done anything like that. So the real patterns are the ones that really have that property, that you can take only the information in the pattern, and that is enough to be like a middle-class, lowbrow Laplace's demon and predict something about the future. Peter Newell says, in a hypothetical scenario where we get to completely rewrite the U.S. Constitution, what do you think about a system where bills are passed into law by an assembly of 1,000 randomly selected citizens? Yeah, this is a known idea, or at least a very close relative of a known idea called sortition. And interestingly, it kind of works in the experiments that have been done. I think Ireland did an experiment. You can go back to the episode I did with Astra Taylor a long time ago on following up on her book, Democracy Doesn't Exist, But We'll Miss It When It's Gone, which is sort of, it was a while ago, but yeah, now we're feeling that, right? So, it can work, and it works basically because 1,000 randomly selected citizens will have some crackpots in there and some unserious people, but most people are pretty serious. And even though they might be randomly selected people who would not be politically engaged in their average lives, the fact that they're chosen for this job makes them politically engaged, and they're actually pretty good at taking these issues seriously. On the other hand, I don't think it's a good idea overall. I think that it's good maybe for some special circumstances, for some special things that you might want to do, some referenda or something like that. But in the modern world, something like the United States is just too big. It's very, very difficult to understand what kind of rules and regulations there should be in a country like the United States. Certainly members of Congress can't understand every single piece of legislation. They cannot possibly understand every single pro and con argument. So they have staff members who do this. They have political party apparatuses who do this. They distribute specialized knowledge among many, many different people, just like a university or a corporation or a movie production company or anything else like that. So I worry about the sortition example, the 1,000 random people, that they would actually have – it would be difficult to reproduce that kind of expert knowledge. Of course, they could hire staff members and so forth, but how do they know who to hire? There is specialized knowledge involved in being an effective legislator in a modern, large, democratic country like the United States. I might imagine, I think that there's probably a compromise here. We do have here in the United States a bicameral legislature, right? We have the Senate and we have the House. Well, what if we just replaced one of those? I don't even know which one would make sense. They're both kind of horrible in their own individual ways. But what if we imagined, I think we could imagine replacing the House with a sortition thing with 1,000 members if we also replaced the Senate with something that was more fairly distributed amongst the population. Then we would have, I think maybe, I'm just guessing, the political scientists could be experts here and chime in. I'm guessing that would be a better system than what we have right now. Qubit says, why is it that a gas in thermal equilibrium is fully specified by the three parameters of temperature, pressure, and chemical potential? Is there a fundamental reason why we can compress the 6n degrees of freedom of the microscopic theory down to 3, or is that just a brute fact of the emergent theory? Well, yeah, I'm tempted to say this is just a brute fact. Or put another way, you're asking a why question. Why is it the case that this is true, right? what is the space of other alternative possibilities that we're thinking about here? Are we thinking of, if the fundamental laws of physics were different? Are we thinking about if, I don't know, space were not three-dimensional, or the Hamiltonian of the atoms were not bounded below? I don't know what it is that the alternatives to the real world might involve, such that we could say, here is why the real world has this property. In general, I don't think that there is a very well-developed theory of emergence, in the sense that when you have this microscopic theory, here are the emergent features of the macroscopic theory, right? That would be nice to have, or even the existence of an emergent macroscopic theory. I don't think that we have that. So this is a very specific example of that. Why does thermal equilibrium have these particular parameters attached to it? There might very well be some deep, slick reason, based in some bit of physics that I just don't know about. But I think it's just a fact about the microscopic theory and the definition of thermal equilibrium. Gregory Kusnik says, should lawmakers face consequences beyond the ballot box for enacting mean-spirited or ideologically driven policies that actively harm national security, the economy, or the lives of ordinary citizens? No, I don't think so. I think that those are just too subjective and subject to abuse if you had rules like that. I do think that legislators, lawmakers, whether in the executive or the judiciary or the legislature, they should all be subject to the law. We've had controversy about that here in the United States. The Supreme Court recently decided that presidents could not be prosecuted for doing illegal things if they said that the illegal things they do are in their presidential duties, part of their presidential duties, right? And that is hopelessly subjective. So that was a terrible, terrible ruling, as many people already agree. But so I think that was a bad idea. But I think that the ballot box is the place for these subjective judgments, and the law is the place for hopefully more objective questions of, did you actually violate a law, one place or the other? Arrow says, your biggest ideas in the universe series is a good example of breadth first teaching. Why is physics usually taught more depth first? I think conceptual clarity over a larger field and set of equations makes it much easier to learn the details and applications later. I feel slightly misled that GR, QFT, and many others weren't even mentioned to me in school, but we spent a lot of time calculating. Well, you're asking another why question, in some sense, right? Why is the history of education the way it is, so that if you're not going to be a professional physicist, the way that you're taught physics is very much like a watered down version of the way that you are taught physics, that you're taught physics if you are going to be a professional physicist. So in other words, we have a pretty good way of teaching physics to future physicists, right? Starting with classical mechanics and Newton's laws, and then eventually we get to relativity, statistical mechanics, thermodynamics, electricity, magnetism, quantum mechanics. There's a whole bit, and you can slightly vary the order of operations there, but I think it makes some logical sense. And the nice thing about that whole thing is that you really learn it. I mean, you learn it. It's not just you're learning some of the highlights. You really learn what Newtonian mechanics says in the sense that you become able to calculate. You can answer questions at a very precise level, plug in numbers. You can get rockets to the moon with a first-year physics education, okay? Plus other more specialized bits of knowledge, to be sure, but you don't need much more physics than that. And that makes it very easy for teachers, as I know, because you can then grade on the basis of doing problem sets, right? You're taught to do problems, you get a grade on the basis of them. For more qualitative ways of learning, where you don't know the equations and the ability to solve problems and things like that, grading is harder. So that's one very down-to-earth reason why it is just easier for in high school or early college for even non-physicists to just be taught the easy but quantitative classical mechanics, Newton's laws version of physics, because it's easy to know when you've learned it. It's easy for the teachers to know that they understand it well enough to grade you. It's easy to provide exams and problems and things like that. The broader scope of all of physics is, I've long advocated that we should be teaching high school students something about gravitation, general relativity, both special and general, quantum mechanics and particle physics and cosmology, things like that, the things that make modern physics very, very interesting. If you wanted to add in there things about biophysics or plasma physics, whatever your favorite thing is, that's fine. We don't necessarily agree on the most important things, but there's no reason to stick to physics from the 17th century when we're teaching high school students physics. But it's harder to do that well. It demands a lot of the teachers, right? They need to know all this extra stuff. It's harder to grade people. And it requires a bit more work to make up the course, right? You can't just take the existing course of physics majors and water it down, go more slowly and cover less material. So there's a whole bunch of very down-to-earth, boring reasons, I think, why physics is taught that way. I don't think it's the right idea, but that's my guess as to why it's true in practice. Josh Charles said, I really enjoyed the discussion of fitness seascapes. They must be connected to energy landscapes in some way. After all, they are still working within the laws of thermodynamics. How do you connect them? Would it be fair to say that the fitness landscape must evolve as a derivative of the energy landscape? So no, it's absolutely not fair to say that. But there might be a connection, although I don't think that the connection is a straightforward one. I suspect it would be a more subtle one. The energy landscape idea, just so everyone knows, is if you have some system like a ball rolling down a hill, or physicists use this for scalar fields in the early universe or what have you, but very often you can just look at the energy of a system as a function of some coordinates. They might be literally the coordinates of where it is in space, or they might be some more conceptual coordinates like the value of a field. And then you say, look, if you live in a world that is, number one, out of equilibrium, so we're not in thermal equilibrium, and number two, you can dissipate, right? So a ball can roll down a hill, but on the way, it's giving off noise and heat and things like that. So the energy of the ball is actually not conserved. That's a crucial element to the fitness, to the energy landscape idea. And what that means, the ability to dissipate energy, is that the ball as a big macroscopic system will generically roll down to a minimum of the energy landscape, and then it might roll around a little bit, but eventually it will come to rest and just sit there. So that's why the energy landscape idea is a useful one. It basically tells you what the future static configurations of the system might be and how they will get there. The fitness landscape idea is obviously analogous. It's saying that, of course, let's be true to the way that the biologists talk about this. They say that a population of organisms climbs to the maximum of a fitness landscape, and the maximum of the fitness landscape is defined by your reproductive fitness, how many babies you're going to have, how much you're good at sending your genes to future generations. So I don't think that one is the derivative of the other. That would say that the minimum. So if the fitness landscape was a derivative of the energy landscape, then the value of the fitness landscape would be zero, where the energy landscape was a minimum or a maximum equally. I'm just not really sure what exactly that would mean. I think, in fact, it's much closer to the maxima of the fitness landscape are, in some sense, minima of the energy landscape, because the organisms that constitute a population of organisms with their little genomes moving around, they are still physical systems, right? They metabolize their open systems, and it's crucially important that they're open systems. So they take in energy from the outside world, they use that energy to metabolize and to move around and things, and they're kind of trying to find a happy homeostatic equilibrium, right? They're trying to find a place where there's enough food to take in and they can survive for a while to take it in and reproduce and things like that. So it might be that there is some way of translating fitness into literally minima of some kind of energy of some sort. The trick is, what do you mean by some kind of energy? Because you're not going to include all the energy. All the energy is conserved. You're going to divide things into the energy of the macroscopic system and some other environmental energy that you can dissipate. I have no idea how that would work. So I think it's an interesting question, but it's not something that has been ever directly addressed by anything that I've seen out there. Okay, I'm going to group two questions together. One is from Will, who says, do you own a bespoke suit? And if so, from where? And Robbie P says, I know you're interested in dressing well in fashion to some extent. So do you have any personal style icons? So these are both, I suspect, these are leftover questions from the wonderful episode we did almost a year ago now with Derek Guy, the fashion guy on Twitter/X, who's now also moved over to Blue Sky, like many people have. And I am interested in these ideas without necessarily being that invested in them. I do think, let's talk big picture philosophically here. I know when I had Derek on the show, I thought he did a great job of being a podcast guest. There are inevitably some grumpy folks who like, well, I don't care about this. This is a frivolous waste of time. This isn't what I signed up for when I came to this podcast, et cetera, et cetera. We both knew that was going to happen. That's okay. It's a free country. You're allowed to vent your frustrations with the world. But to me, I think that there's part of life which consists of aesthetic pleasures of all sorts, whether it's food or film or novels or works of art or how you dress. Right? These are all choices about the appearance and artistic values of the world that you're allowed to care about or not, okay? But I care about them, and I think that many people do. I think that it's absolutely the right attitude to have to try to make the world beautiful as much as you can. It's not the only thing that you're going to try to keep in mind, right? Comfort and expense and convenience, these all are also perfectly good criteria that should inform how you choose to dress. But I think that it is overall a valorous, positive thing to try to dress in aesthetically appealing ways. Okay, that's my big picture thing here. Of course, for every individual person, they're going to have to decide what that means. There's also, as Derek constantly points out, there's a cultural context here, like a person who is completely mildly, mediocrely, uninterestingly dressed in one context will completely stand out and look weird in another context, right? Whether it's what society you're in or even what kind of event you're going to. You don't dress the same for the opera and a football game, even if you're the same member of society, okay? So those considerations also count. So it's very complicated, and I don't judge people on how they dress that much. As long as they don't judge me, then that's fine. Having said that, so I am interested in dressing well overall. Certainly not interested in fashion in the traditional sense of, it depends what you mean by fashion. If by fashion you mean what is fashionable, that is to say, if you're really into clothes and dressing well and fashion in the super serious sense, you might care a lot about the difference between what is considered fashionable this year versus last year. One of the things I like about Derek's take on fashion is that he doesn't care about those things. He likes a lot of new stuff, but a lot of old stuff, and he doesn't like the new stuff because it's the new hot thing. It's because it works or it doesn't, right? So I have zero knowledge or interest in fashion as a trend kind of thing. I think that dressing well could be more or less not timeless is certainly an exaggeration, but not an of the moment kind of thing. Something that is more or less there's similarities. There's a sense of dressing well that transcends the season to season variation in people's tastes and what gets sold in stores. Okay, but I have not ever bought a bespoke suit. No, I have not. I would like to someday. That would be great. They're not cheap, and I don't have time, and et cetera, et cetera. Wearing suits is not something I do very much, right? So I have suits. I like the suits that I have. I probably have enough suits to last me for a very long time without buying any new ones, honestly. Maybe the next time I feel the need to buy one, I will go bespoke just for the intellectual interest, among other things, of being through the process and seeing if it really does make a difference. I have people who are friends of mine who do wear bespoke clothes all the time, and they love it. But there's always a self-justification thing. I mean, they would say that they love it, but they don't feel regret from spending all that money, depending on who they are. In terms of my personal style icons, not really. I'm not nearly that. I don't spend enough time thinking about it to have style icons. But the question brought up a joke I told on Twitter like 3 years ago now, when it was still Twitter. I mentioned, because I'd already, a little bit less than 3 years ago, so I had made known that I had accepted the job at Johns Hopkins and was going to move here to Hopkins and would now start teaching again. When I was at Caltech, I didn't do that much teaching. So I said, so it was half jokingly, I said, I gotta, figure out how to dress as a real professor now, standing up in front of the students once again. And as my style icon, I suggested Dylan Reinhardt, who you probably don't know about. It's a fictional character. He's a professor played by Alan Cumming on the TV show Instinct from a few years ago. And it was a fun little show. It's not serious or deep or anything like that. Alan Cumming is an amazingly good actor. One of these people who, when he's on the screen, you're watching him. He's very charismatic and compelling. And he played a psychology professor who helps the police solve crimes. Okay, it's a very standard kind of tropey show. But I loved his clothes. His clothes were amazing. He would always dress up. He would always wear a suit and a vest and a tie and a pocket square and a scarf and whatever. And they were always combinations of colors and patterns that my feeble fashion sense would never have come up with, but they always worked very, very beautifully well. So as a joke, I said he was going to be my style icon, and I put up some pictures of him looking very good, very dapper in this TV show. It wasn't a great TV show, but by the way, it did, I think it got some attention because it was the first drama on network TV where the protagonist was gay. Certainly the first one where the protagonist was gay and married. So Dylan Reinhardt, the psychologist, was a married gay man, and it wasn't played for a big deal. It was just yeah, okay, he's gay and he's married. That's what it is. There's his husband. They have a pretty loving relationship. They don't always agree, just ordinary stuff. So that was very nice. But anyway, the punchline of the story is I wasn't really planning to dress like Dylan Reinhardt, although maybe I should still aspire to that. But someone else, responded to the thread saying oh yes, Alan Cumming, he's great. I love him. I wish I could dress more like him. And Alan Cumming himself showed up in the thread from his Twitter account to say, "Thanks so much. That's very sweet. Just so you know, it's a TV show and people dress me for that. I don't dress like that myself from a day-to-day basis." And I went and, he put a link to his own, if I remember this correctly, he put a link to his own Instagram feed, and you can click on it, and it's absolutely true. He's not by himself. Bless his heart, Alan Cumming, a style icon. Usually he's not wearing very many clothes at all. He's by the pool or whatever. Or dancing in T-shirt and jeans or something like that. So, my style icons don't even exist in real life, but maybe that's just for the best. Tim Giannitsos says, can you talk about why entropy increases in terms of phase space? If we think of a system in terms of a region of phase space, I think an entropy increase corresponds to the region increasing in volume over time. But I heard Liouville's theorem basically says that a region should stay the same volume over time. What am I misunderstanding? You're not misunderstanding anything, but you're just missing a crucial ingredient, which is the coarse graining of the system's state, or let's say the system's probability distribution. So phase space is absolutely the correct way to think about entropy. Not only can you, but you should think about entropy. You should not think about it in terms of configuration space, right? In terms of where things are. Phase space is configuration space plus momentum space, and momentum is just as important here as the configuration. That can lead people to get things a little bit wrong sometimes. So Liouville's theorem, you're exactly right. If you start in phase space with a probability distribution that is defined within some boundary, some region of phase space that says, well, maybe the system is in here, but I know it's not outside. So, that defines a certain probability distribution. And then you say, I'm going to use the equations of motion to evolve that system over time. You do that. Liouville's theorem says that the volume of that region of phase space that you originally defined stays constant, basically because every single point in one point in phase space goes to one point in phase space later on under the equations of motion. So the same number of points go to the same number of points, so the volume stays constant in a certain way of measuring volumes on phase space, etc. And the entropy is indeed related to the volume of phase space. So how can it be true that entropy goes up even though the volume is constant? The answer is you're supposed to forget details about that volume. The point is that in very realistic evolutions, the volume of phase space that you get by starting with an initial compact region that is not zero volume, but is small volume, and you let it evolve, it will become very, very spread out in terms of becoming very skinny and tendril-like while the total volume inside remains constant, right? So if you step back and squint at it, it looks like it's diffusing all over the place. Think of, a set of atoms or molecules in a box of gas. Think about, them all being imagine the whole box is full, but you have a little bit of atoms in one corner, okay? You let them diffuse. The number of atoms doesn't change, but you don't know exactly where the individual ones are going, so you kind of lose information over time. And to you, it looks like the atoms are just spreading out, even though it's the same number of atoms you had before. That's an analogy for thinking about the Liouville's theorem spread in phase space. The actual volume of phase space you start with remains constant. But if you coarse grain by saying, I don't know exactly, let's just take a box in phase space and average over that sized box, okay, for many, many little boxes, then the apparent volume of where you are in phase space and the associated entropy will increase in time. So coarse graining is absolutely crucial to this notion of entropy. Water says, how did Newtonian physics explain the sensation of acceleration at Earth's surface, given that gravity and the normal force cancel out? I've often heard this attributed to gravity being a body force that doesn't generate internal stress. By that logic, shouldn't electromagnetic force generate the same sensation as gravity? I'm a little confused by the last part, by the electromagnetic thing, but I don't think it's that mysterious why Newtonian physics explains the sensation of acceleration. The sensation of a force pushing on you due to gravity when you were just standing there, standing still on the floor. I presume that is what we are talking about. The force acting on you, there's a gravitational force on every single atom in your body, but there is the normal force from the floor that is only pushing on your feet, right? Only on the soles of your feet. So as a result of that, you are squeezed. There's two things that are happening. One is that you feel the gravitational force on your feet, okay? If you stand up for a very long time, your feet will start to get sore for exactly that reason. But also your whole body feels that you're a little compressed because your whole body is being pulled down and only your feet are being pushed up. That squeezes you a little bit. That's the origin of the sensation of acceleration. I don't know what exactly you mean by the electromagnetic bit because in a human being, we're half positively charged particles and half negatively charged particles. So there's no direct analogy to that in a very realistic situation. Anonymous says, one thing I've been curious about for a while is the usage of the word real in physics, specifically in the philosophy of physics. I've heard you use this word a handful of times, but I do not know what it means practically. What qualifies as real, and when should one use the word real when referring to physical systems, observables, etc.? Well, yeah, that's a very, very good, contentious question. People disagree a lot about when to use the word real. I think that like many other words, like entropy, like life, this is one of those words that means more than one thing, and there's different contexts in which it makes perfect sense, but something that is applicable to one context might not work in a very different context. So for example, so I think that's probably where you should leave it. You should probably actually take that answer as correct. It depends on the context, okay? Within some context, things that are real are generally those that are unavoidable. Their effects are unavoidable. They're not optional. So for someone like me who does particle physics, field theory, general relativity, we always talk about coordinate systems or gauge choices not being real, right? These are choices made by human beings. If I want to have, some objects in a room and you say, well, where are they? And I say, okay, let's set up a coordinate system and I will tell you their X, Y, and Z coordinates. There's a very real sense in which the positions of the things are real, but the coordinates are not. And that sense comes down to the fact that someone else could have used a different coordinate systems and encoded a different coordinate system and encoded all those positions equally well. It's not X, Y, and Z or R, theta, and phi that are real. It's the actual positions that are real. We just have multiple ways of representing them. So to a physicist, I think that's what it very often comes down to. Like, what is true under any way of describing the system, any way of thinking about it, that those aspects are real. There's more down-to-earth aspects, right? Are ghosts real? Like ghosts in the sense of the spirit of my living soul after I die. Well, I don't know. Do ghosts have an effect on the world? Can they do anything at all? Are they predicted by some theory? There's a whole bunch of different questions that you could imagine asking. So I think the very short answer to your question is you're right to be confused because there is no one once and for all definition of real. It's going to depend on the context that you're talking about. Brendan Barry says, my understanding is that ADS-CFT shows that a quantum gravity description in an anti-de Sitter spacetime is dual to a quantum field theory in one less dimension on the boundary of the ADS spacetime. I've recently seen research reporting the testing quantum gravity in the lab by using quantum computers to simulate the QFT side of ADS-CFT and mapping the result to a theory of quantum gravity in ADS. This is fascinating to me. However, obviously ADS does not describe our universe. Do you see this research as quantum gravity in the lab? Do you believe ADS-CFT will lead to a deeper understanding of our universe, or is it just an interesting mathematical duality? Those are two very different questions. I should have chosen one and not let you ask both of them, but it's too late now. I've spoken them both out loud. I don't think that's quantum gravity in the lab at all. I think that there's many examples of cases where you have some physical system and you say, I think the physical system is described by these equations. And then you come up with a different physical system that is also described by those equations, and you do experiments on the second system. Of course, that's not experimentally testing the first system because it all depends on whether you were right when you said that those equations describe both of them. If you are right, you didn't need to do the experiments on the second system. You could just put those equations on a computer and solve them, right? The point of doing experiments, in my mind, is as a reality check because we don't know whether our equations are on the right track or not. That's why experiments are very important. You can't just say, the classic example, this ADS-CFT example you're using is a close relative of a very common example where people talk about Hawking radiation, okay? For Hawking radiation from black holes, it turns out the equations that we use to describe Hawking radiation are very analogous to certain equations you can write down in the right circumstances in fluid dynamics. You could even quantize them and get phonons appearing from a so-called event horizon and so forth. And that's fun to do, and maybe you will learn something because maybe the physical phenomenon sort of does the simulation better than your computer does, but it's still a simulation of the black hole. It's not actually real-world black hole physics. So no, it is not quantum gravity in the lab. Do I believe ADS-CFT will lead to a deeper understanding of our universe? It's taught us some things. It's not directly applicable to our universe, but it's absolutely very possible that it will end up being indirectly applicable to our universe if we understand more about dualities and gravity and wormholes and non-locality and holography and complementarity better, then that would be great. So I think it's good that people are doing it. I do think it gets a little more attention than maybe it deserves because it's doable. When scientists do work, part of what they do is because the question is interesting. Part of it is because they think they can make progress. And ADS-CFT is a classic example where progress is makeable, and therefore people are working on it, maybe a little bit more than it deserves in terms of how much it will teach us about the world. Anonymous says, during your time as an undergrad or grad student, did you ever question whether or not continuing with college was ever worth it? To be honest, no, I never did. When I started as an undergrad, I had hilariously little idea what the whole thing would involve. I didn't have any role models or anyone really telling me what the whole thing was. I didn't know what it meant to go to grad school, et cetera. I mean, I knew that grad school was involved, but I didn't know, what it would mean to apply to grad school or how you get in and things like that. But I knew that's what I wanted to do. And I enjoyed college and I enjoyed graduate school. Parts of it are very, very hard. Parts of it are depressing. Sometimes projects don't work out. Sometimes things happen that you don't anticipate. That's always true. But I was always, for better or for worse, fortunate enough to know what I wanted to do and have that be pretty clear in terms of what I should do next. If anything, My shortcoming was that it was just so obvious what I was supposed to do next. I didn't think it through, right? That I never really deviated from what I wanted to do for many, many years on end. And it would have been absolutely sensible for me to sit back and think very carefully, even if the answer came out to be, yes, you're doing exactly the right thing. I never really put very deep thought into alternatives, which I think I do encourage young people always to do. Like, how do you know when you're 20 years old what you want to do for your life? That's a big ask. Ken Wolf says, I was interested to see that you are also a fan of the Open Worm project. My main takeaway from what I've heard about this project is the profound gap between the challenge of simulating something with 302 neurons. It says neutrons, but it's actually neurons we're talking about here, and the notion of simulating something like a human brain. It seems to me that we are very far from contemplating something like even an open fruit fly project, let alone anything at the human level. Watching the progress of this project, you draw a similar conclusion. The short answer is yes, I draw a very similar conclusion. For those of you who don't know, the Open Worm project is using the fact that scientists have mapped the complete connectome of the worm C. elegans. It only has 302 neurons, and the connectome is the wiring diagram, the way that all the different neurons talk to each other, get inputs and outputs. And okay, so you've done that. Do you now understand the brain of the C. elegans worm? No, you do not, because you don't understand what the individual neurons actually do. And there's a lot of computing power, like Ken says, to go into even simulating it. So doing it for larger organisms is going to be a challenge, absolutely. So you still got to make progress. It's not like, oh, we'll spend a couple of years and a couple of dollars and we'll understand the human brain perfectly. It's going to be much more gradual than that. We should have a podcast about this. This is an interesting topic to talk about in greater depth. Michael Lesniak says, I love the cocktail and martini discussions. As a bourbon aficionado myself, I'm curious what bourbons you like. Do you have a favorite or a go-to for an old-fashioned or Manhattan? I'm not a super bourbon expert. I did a little taste test for myself some years ago, and there's a bourbon I really like, and I'm forgetting what it was. Angel's Envy or something like that. Angel's Wings. There were angels in it, but I've never been able to find it again. It was not like some tiny bespoke thing. It was made by a giant distillery. But apparently it's not as common or not as popular as I thought. There was a Mindscape listener who actually sent me a bottle of bourbon. I'm sorry, I just apologize because I forget both the person's name and the name of the bourbon, but it was super good. I don't encourage people to send me bottles of bourbon, but sometimes people don't want to join Patreon or whatever, so they need to be clever, and I appreciate that sentiment very, very much. So the short answer is I do not have specific bourbon recommendations for you, although I do think that people who like spirits but don't know a lot about bourbon should absolutely try very good bourbons. Very good bourbons are, sophisticated and elegant and interesting in a way that very bad bourbons are not, if that's something that you might be interested in. Also, parenthetically, I'm not an old-fashioned person. Old fashions, I don't like drinks where you basically rely on sugar or fruit juice to make the drink interesting. Given that I don't have cocktails that often, when I have them, I like the mixture of the alcohols, the spirits, to be doing most of the work. So I like martinis, Manhattans, sidecars, corpse revivers, things like that. A little fruit juice is fine, but I don't want sugar as like an ingredient. An old fashioned has generally simple syrup in it, which is basically sugar dissolved into water. No disrespect to anyone who loves the old fashions out there. As I often say, this is a completely subjective thing, but I'm definitely a Manhattan guy. Manhattan or just bourbon straight, I'm very happy to take. Connor Shaffrin says, by some accounts, as many as 1 out of 3 users on X/Twitter may be disinformation bots, and other platforms may be heading in the same direction. At the same time, AI video and voice, as well as other deep faking technologies, are nearly to the point where normal people can generate videos of anybody they want, saying anything they want. And at least in the US, a disturbing number of people no longer trust legacy news media and instead get their news from unverified internet sources. What on earth, if anything, can we do about this? Is the post-truth era an inevitable side effect of technology? Well, I would like to know. Yeah, I think that there's been a lot of pontificating about this issue, and I think that it's a super important issue. Absolutely do not want to downplay the crucialness of understanding what to do about this, but I don't have any great ideas myself. I do think it's something we should take very seriously and think about. You don't want to get into the business of banning different kinds of information sources unless they're, doing something blatantly illegal or something like that, but you want to let all of these things find their niches. And, we should also not overly romanticize the past. Way back in the day, it was very common that newspapers and broadsheets and so forth would be highly partisan and polarized and sensationalized and fake news, if you want to put it that way. And there was only like a medium-sized period where we had broad communications channels that were sort of universal and more or less tried to be objectively true. Right, that was a standard for a little while, but it was not the forever standard, and it seems to be going away. I mean, there are still institutions that try to do that, but two things happen. Number one, they have competition from more ideologically oriented outlets, which sacrifice objective truth sometimes to flattering their user base, let's put it that way. And the other is that, of course, even if you try to be perfectly objective and try to just tell the truth well, you're going to be pilloried by the people who you say bad things about, right? And so places like the New York Times or whatever, which absolutely have their problems, are, disregarded by a large fraction of people, mostly for ideological reasons, rather than, the New York Times publishes a tremendous amount of stuff every day, and it's not hard for any one person to find things in it to disagree with. And if your standards are, if something appears in there that I think is wrong, then I'm going to, cancel the newspaper or whatever, then nobody would subscribe to the New York Times. And that becomes a problem. There's a third problem now that I'm thinking about it. I mean, I want to be fair to critics of the New York Times. It did a terrible job. The New York Times, Washington Post, many institutions have done a terrible job responding to the changing political landscape, in the sense that there are norms of political discourse that have been believed to hold or held pretty well for decades, if not centuries, that have been challenged and overturned by recent events. And I think that the political journalism as a field did a very bad job in covering these developments accurately and fairly. You can't act like it's politics as usual when it's not. And, they normalized a lot of really non-normal behavior. And I think that will go down in history as a very big failure of the mainstream media. But I'm a huge believer in the mainstream media as an institution. I want it to succeed. I want it to be good. And so when I criticize it, it's because I want it to get better, not because the mainstream media itself is antiquated or useless. We need something called the mainstream media. We need something that aspires to just tell news as objectively and fairly as possible. That doesn't mean both sidesing everything, because objectively and truthfully sometimes means one side is wrong, right? Jay Rosen and other people have made this point over and over again, that a lot of modern media replace objectivity with, we just report what the different political actors say. That's not what objectivity is. Objectivity is doing that and also saying, but this one is objectively correct and this one is objectively false. So anyway, I'm wandering away from Connor's actual question, which is, the bots and everything. They're a big deal. Literally earlier this morning, I blocked a bot on Blue Sky, which was literally set up it was clearly a large language model. It was clearly an AI bot that would pick out individual skeets, they call them, on Blue Sky, or posts, or whatever you want to call them, and just criticize them, right? You could tell it was AI because you look at its page and like every 5 seconds it has a different response to a completely different person about a completely different topic, just being insulting and critical, right? Very, very easy to do, not that hard to write an LLM to do that kind of thing. And of course, if you put more effort into it, you can create false narratives, create evidence for your false narratives, and so forth. The era in which video and images were taken as more or less reliable evidence for things has passed, right? When things become crucially important, it will be very easy to either fake actual evidence or undermine actual evidence by saying that it's fake, even if it's not, right? So a new equilibrium is going to have to be reached. And I do worry that it'll be too easy for people to find information sources that are entirely unreliable, but that they take as gospel. And it's not that people are in silos. I think that's a misdiagnosis of the issue. People who have studied this have found that people on one side or the other of the partisan divide generally are exposed to the points of the other side. It's that they just filter them out personally. They just don't listen, right? It's a human problem that technology is taking advantage of rather than a technology problem that humans are being victimized by. It's still a problem one way or the other, and I don't really know what to do about it. I think that we're going to have to this is something where it's going to be hard to think of the solution ahead of time. We're going to have to work out the solutions in real time, what to do about it. But I absolutely believe that we're going to need to look for solutions here. Eugene Brevdo says, you said something a few months ago that intrigued me, but not sure how to reason about it. Paraphrasing, there is a natural reference frame for the universe. It's the CMB rest frame. This brings two overlapping/related questions. First, if our planet were X billion light years away from where it actually is, would we see exactly the same CMB given the rate of expansion of the universe? And two, is the CMB rest frame calculated, e.g. by least squares or similar, to minimize some average squared redshift loss? And if so, is the loss anisotropic? And do the answers provide evidence for, against, or neither that we're in a finite universe? So a lot going on here. I think that there's some misunderstanding. I'm not completely sure what's going on in some parts of the question. So I'm going to try to answer my usual strategy to try to say true things and hope that they come close to the answers you were looking for. By the CMB rest frame, what we really mean is that the CMB does not come from a place. The CMB comes from a time. It comes from the time in the history of the universe when electrons and protons recombined for more or less the last time, and the universe became transparent about 380,000 years after the Big Bang. It happens all throughout the universe, okay? All throughout the universe, which is more or less homogeneous and isotropic. The universe is expanding, it cools off, the atoms recombine, and we now have photons freely streaming throughout space. So at any one point in the subsequent universe, you look around and you see a whole bunch of photons. You see a whole bunch of photons that were last emitted at that moment in time that we call the surface of last scattering, where the cosmic microwave background was made. And roughly speaking, due to the actual fact that the universe was homogeneous and isotropic, you will see an isotropic set of photons coming at you. You will see, in other words, the same number of photons at the same frequencies coming at you from all directions. Now, there's an obvious caveat to that, namely, that can only be true in one reference frame. That is to say, for one, forget about reference frames. It's a mistake to sort of extend your reference frames throughout the universe. Just think about the motion of a single observer, okay? There's something called the Doppler shift. So if it's true that there is a way an observer can be moving such that all the photons coming from all directions look to be at the same temperature, then if you are moving with respect to that observer, some of the photons are going to be blue shifted, the photons you're moving in the direction of, and some of the photons are going to be red shifted, the photons you're moving away from. So there are many, many ways to move in the universe so that the cosmic microwave background looks not quite isotropic, because you're moving with respect to it. And there's one way to move so that it does look isotropic, and that's the rest frame. So if you extend this throughout the whole universe, at every point in space, at every moment in time, there is a way to be moving so that the cosmic microwave background looks the same temperature in all directions. That is the cosmic microwave background rest frame. So I'm not sure what minimizing some average squared redshift loss or anything like that means. It's just a matter of redshift and blue shift. And indeed, we here on Earth are not moving exactly in the cosmic reference. Rest frame. We are moving with respect to it. So there is a dipole anisotropy in the cosmic microwave background that has been well mapped out. When you say if our planet were billions of light years away, what would we see? It depends on when, right? It depends on when you're looking. The cosmic microwave background is cooling off as the universe expands. But if you're looking at the right moment, you would see, yes, an isotropic cosmic microwave background at the right temperature. Of course, when I say isotropic, it's not 100% isotropic. It is statistically isotropic, but there are tiny fluctuations, 1 part in 100,000, very, very tiny, that become very important to modern cosmologists to map out those fluctuations because eventually they grow into galaxies and stars and things like that. Finally, none of this has anything to do with whether we live in a finite or infinite universe. Well, it has a tiny bit to do with it in the sense that if we lived in a very small finite universe, you would be able to tell from observations of both microwave background and other things. Indeed, the simplest way to tell would be that you would see a galaxy and then you would see another picture of exactly the same galaxy, but it looked like it was further away, right? Because photons from that galaxy had wrapped around the universe more than once before getting to you. There's zero evidence for anything like that. If it happens that the size of the universe is just about the same order of magnitude as the horizon size cosmologically, that is to say the total distance out to which we can see before we see the cosmic microwave background, then there are subtle clues you might be able to notice in the anisotropies of the CMB, not in the overall fact that there's a rest frame. That has nothing to do with it. But anyway, we don't see those signs anyway. But the reality is, all that means is that if the universe is finite, the size of the universe is bigger than the cosmic horizon size right now. It says nothing about whether or not it is finite or not. Maybe the universe is infinite. Maybe it's finite but just bigger in size than our current horizon size. That's completely plausible. In fact, you got to keep in mind it's entirely possible that it is much bigger than our current size, but it's not homogeneous and isotropic on very large scales. So you just can't take the reasoning that we apply to homogeneous isotropic cosmologies and blithely apply it to the universe as a whole. There's no evidence that that would be a good thing to do. Finally, let me mention that the fact that there is a cosmic rest frame is kind of a puzzle that nobody talks about, right? It goes in with the puzzle that we don't know what happened at the Big Bang and why the Big Bang happened in the way it did. It's low entropy, among other things. That's a semi-well-known fact. It's not as well-known as it could be. But the fact that there's a rest frame is another kind of puzzle because the laws of physics don't have a rest frame. So what is it that chose the cosmic rest frame at early times? These days, the state of the art is we just put it in as an initial condition. But it's one of those why is it like that questions that may or may not have an interesting answer ultimately. Anonymous says, is there a cohesive moral argument for the value of a human life outside of its concurrent relationships with other humans? I think that most people would say that ending someone's life is wrong, even if that person lives on a remote island with no relationships and their experience of death is so swift that it is imperceptible to them. However, I struggle with how to produce any logical argument as to why this would be a bad thing, given that it has no perceptible impact on any conscious mind. As I've often said here, I don't have a once and for all moral theory that I can unapologetically put forward and defend. It's not that I don't see arguments for and against various different approaches to morality, but I see all of them. They all sound good, including the criticisms of each other's moral theories. I guess the one point that I think can be made that is not often made is that a lot of moral theories or moral intuitions come about by comparing either reality to a hypothetical different reality or one possible future to other hypothetical possible futures. So, in other words, comparing against possible worlds, including comparing against different times in different possible worlds, is an important part of morality. So even if there's only one person around, that person can say, I would rather exist tomorrow than not exist tomorrow. And in that sense, it's not really moral because that's the only person. It's not being able to act on other people, but it's fair to say that that person is legitimate in wanting to live another day, even though if they died, they wouldn't be around to regret it. In yet other words, I don't think that the right way to think about morality is to skip to the part where the person doesn't exist and then say, well, they don't regret it, so it can't be bad, right? You can regret a condition at time X at some previous time because we have in our minds the capacity to hypothetically imagine counterfactually different things that could happen in the future. So it goes back to, discussions we've had many times with people like Malcolm MacIver, Adam Bully, and others. Human beings contemplate different moments of time. They contemplate different possible worlds, different hypothetical scenarios, and a lot of the oomph of morality comes from saying, I like this scenario better, this one is good, that one is less good. So I don't think it necessarily relies on having relationships to other humans. I mean, when it comes to in practice, if there were literally only one human on Earth, then I would grant them the right to do whatever they wanted with their lives. I don't think it would be morally wrong for them to end their life or continue their life or whatever. I think I would, let them do what they wanted since they who am I to tell them what to do if they're the only human being left on Earth? Okay, I'm going to group a bunch of questions together here. Well, only 3 of them, but they're medium long. So they're all about what happens inside black holes. Sean Gallagher says, I've heard a few times that nothing special happens when you cross the event horizon of a black hole, and tidal forces are relatively weak for supermassive black holes, so you wouldn't necessarily notice them as you cross. But that can't be exactly correct, right? If you were to launch me on an orbit where I'm just skimming around the horizon, I'd surely notice when I reach my hand out in one direction and I don't get it back. So then Mark Slight says, falling feet first into a stellar mass black hole, from the point of view of my eyes, would I see spaghettification of my lower body, or would it rather be a matter of seeing a gradual redshift, my feet being the most redshifted? By see, I don't necessarily mean that we're still alive, or that it happens slow enough for us to register it. David Lindsay says, you recently answered a question about the temperature of a black hole. Your answer involved Hawking radiation, and I admit that I didn't fully understand the explanation, but I got the impression that the answer was, although it could not be directly measured, the Hawking radiation would not be particularly hot. From my naive perspective, a place where not even light can escape sounds essentially like a perfect greenhouse, with starlight falling in or more extremely radiation from an accretion disk. Why isn't the answer something on the order of really, really hot? Okay, so all of these have to do with, they're different questions, and I'll try to give them different answers, but they all have to do with the weirdness of the existence of black holes. And black holes are things that, we don't come across in our everyday lives. They're outside our intuition, so we have to actually think carefully about what is going on. Let's do Sean Gallagher's question first. Why can't you just put your arm into the black hole and not get it back? If you're really, really close to the black hole, really right there up against the event horizon, one of the things that is hard to really internalize is the fact that the event horizon is a null surface. That is to say that it is, for all intents and purposes, the event horizon is coming at you at the speed of light if you're right next to the black hole, okay? Now, you might say, but I don't need to fall into the event horizon if I'm outside of it. That's true. You can accelerate away from it at the speed of, or not at the speed of light, but you can accelerate away from it so fast that the light rays that define the event horizon don't catch up to you. Okay, you can do that. It's not a great analogy to take too seriously, or it's not a great image to take too seriously, because a real set of light rays coming at you, you would have to eternally accelerate to escape from them. The black hole has some finite size, so you can accelerate away from it for a little while and escape from it. But if you're right there, right next to the event horizon, that is exactly what it is like. So it's not that, you put your arm across the event horizon and then it gets pulled, ripped off of your hand or anything like that. It's that either when you put your arm across the event horizon, either you fall across the event horizon yourself because the event horizon is coming at you at the speed of light, and then you're inside the whole bit, arm and everything else. Or your arm is in there and you want to accelerate away from the event horizon, so you accelerate so fast that your arm, in fact, is pulled off. Those are the choices. So you would absolutely notice when you reach your hand in one direction and you don't get it back. But that's your fault because you've been accelerating so fast that your body got ripped apart, okay? The more normal thing to do if you just fall in is that you don't notice anything at all because you and your arm and everything else have fallen into the black hole as one piece. Once you're in there, we get to Mark's question about the spaghettification. One thing that I've often said, and it still remains true, the singularity of the black hole is not in the middle of the black hole. It is in your future once you're inside. The best way to think about being inside the black hole is it's kind of like being in a reversed Big Bang, kind of like being in a big crunch. The whole universe is collapsing around you. And so all of you will be squeezed into nothingness. Now, that's not a perfect analogy either, because in the Big Bang, or in your mind, if you're imagining a big crunch, there's an important feature that it is homogeneous, as we just talked about. Matter is evenly distributed everywhere, and so you just see everything crunching around you. In the black hole, that's not true. There is, like it or not, there's sort of a thing that collapsed to make the black hole that has a direction. It's over there. There's empty space everywhere else. So the collapsing into the future singularity is not homogeneous and isotropic. It does happen faster in some places than in others. It happens faster, closer to what you would call the middle of the black hole. Okay, those are just true facts that maybe hopefully help people understand what it would be like to be inside. But what you see, it's hard to explain. I guess the thing I should have said up for the previous question also is, any one of these questions is absolutely, the intuition you need to understand it is absolutely helped by thinking of a space-time diagram of the black hole, okay? This is not how people usually think. You think of like a big black thing. You think of a big ball, like a big, hole in space. You think of the spatial extent of the black hole at one moment of time, okay? It is much, much more clarifying to think of the space-time diagram. You might not be used to thinking of space-time diagrams. I can recommend a good book where you can read about them in exactly this context, which is Space-Time in Motion, the first edition, the first volume of The Biggest Ideas in the Universe. Because then you see, like, oh, yes, there's this surface that is moving at the speed of light where I can't, it's a null surface. The light cones are tangent to it. Once I'm inside, I can't get out. Like, it's just, everything seems much more clear. So when you talk about seeing the spaghettification, I'm hesitating because, I don't know, it depends on where you're looking. But of course, things are moving at the speed of light when you see them. So you have to look at your feet as they were a little bit in the past. Right? Does that make sense? Because it takes time for light to get from your feet to your eyeballs. But if everything is very big, well, let me say it correctly. If everything were very big, then spaghettification would be very mild. Spaghettification only becomes important when you're very, very close to the singularity, and that's exactly where all these details about the speed of light, etc., start to matter. So the question of what you would see is actually a tricky one that I'm hesitant to answer carefully because I never sat down and worked it all out. What you would really do is you would feel the spaghettification before anything else. It's just like we talked about earlier with the Newtonian gravity example. You feel gravity here on Earth because you're squeezed a little bit. You would feel spaghettification very, very vividly because you're being pulled apart, because the gravitational tidal force on your feet and your head are very different, and so that you are stretched. You would see what you would see, not even a gradual redshift. The redshift depends more on the sort of temporal relationship between your feet and your head. So I think you would see a redshift, but I don't think that that's anywhere close to the most interesting or vivid thing that would be coming into your central nervous system about the process of spaghettification. And to David's question, I think here the mistake is thinking of the exactly thinking of the black hole as an essentially perfect greenhouse. Basically, what David is implying is that all the light of the universe comes into the black hole and it sort of rattles around in there, and you would see it all. Isn't that very bright? But it doesn't. When you are looking out, when you're in the black hole, whenever you look out into the universe, if you think about it in terms of space-time diagrams, you're looking into the past, right? You've been told this before. Everything you see is something that happened in the past. You're not seeing things right now, strictly speaking. So there's a direction in which you look out, which is the direction that you fell into the black hole from. And there you're just looking out at the universe. You would see stars, you would see empty space. It's not anything weird, right? You would just look at the universe because you're seeing light from the past that has fallen into the black hole. Once it's in the black hole, it doesn't rattle around any more than it rattles around anywhere else in space. Eventually it will hit the singularity, or it will be absorbed by something or whatever. But the vision that you have inside the black hole of your immediate surroundings isn't that different from the vision you would have outside, to be perfectly honest. Details matter. Details matter on the size of the black hole and how fast you're moving and what the black hole was made of, and all those things really, really do matter. But it's not a sudden change from going inside to outside to inside, I should say. Philip Stickney says, thinking about your solo podcast on emergence, is a given branch of the wave function an emergent property of the entire wave function? And if so, how does that help the way we can think about our entire reality as emergent? Seems to be the biggest difference between other interpretations of quantum mechanics. Yeah, absolutely. In fact, David Wallace, former Mindscape guest, wrote the definitive book on the many worlds interpretation of quantum mechanics. And the title of it was, wait for it, The Emergent Multiverse. And this is exactly why that was the title, because he is not just like a accidental similarity. He is very, very specifically saying that branches of the wave function are emergent properties. They are higher level, coarse-grained things that we get from tracing out an environment, blah, 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 blah. And then you get a simpler description at the higher level in which each branch looks mostly classical with some occasional quantum fluctuations and things like that. And the wave function as a whole still looks entirely quantum mechanical. I don't know what you mean by entire reality as emergent. In this picture, the entire reality is the wave function of the universe. Individual branches are classical emergent properties. Laurel Pepin says, I'm looking for my next tattoo and I want it to be an equation. Do you have a favorite equation you can share, including why it's your favorite? Yeah, I think that it depends on how elaborate you want to be. Like, I'm not a tattoo guy, so I don't really have a level of understanding of how painful it is to get a very elaborate equation. I think there's two very, very obvious choices. One is Einstein's equation. Einstein's equation is awesome. R mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. That is the central equation in the most beautiful physical theory ever invented, Einstein's general relativity. You could do much worse than that. It encapsulates the expansion of the universe, black holes, gravitational waves, deflection of light. There's a lot going on there in that little equation. The other one, of course, is some equation representing quantum mechanics. There you have more choices. You know, if you wanted to be cheeky for the general relativity case, you could do something like the geodesic equation. That's a little bit more esoteric than Einstein's equation even. I don't think the geodesic equation made it into my book, but it wasn't highlighted there because we didn't solve it or anything like that. That's just the equation that says says this is a path that maximizes proper time. This is the path that freely falling objects actually move on. Anyway, for the quantum case, to me, the obvious thing is the Schrödinger equation. The maximally abstract version is capital H with a little hat over it times the ket vector psi equals I times d by dt of psi. You can look it up again, in volume 2 of The Biggest Ideas in the Universe, etc. But there are other equations that would also do a very good job of capturing quantum reality. You could do the path integral equation from Feynman. Capital A equals the integral of e to the I s over d phi or something like that. There's different versions of the path integral equation. Or you could do something like the uncertainty principle. Delta x, delta p is greater than h bar over 2. Any of these equations are great, attempts to really capture something absolutely profound about the nature of reality. The final thing, of course, is there's always the second law of thermodynamics. That's a classic. ds dt, ds divided by dt is greater than or equal to 0, or just S equals K log W. S equals K log W is the definition of entropy, S, in terms of the volume of phase space W contained within a macro state. And that equation has the extra sort of world historical oomph that it is printed on Boltzmann's tombstone in Vienna. So I don't think that Boltzmann himself ever actually exactly wrote down that equation. I think that was Planck's way of formulating Boltzmann's equation, but it's a very good equation. It's the equation of coarse graining and the definition of entropy that takes you pretty far if you want to get a tattoo there. Andrew Goldstein says, physics has theories where the future can influence the past. Since your explanation of unintuitive concepts have been the easiest for me to wrap my head around, can you give me your take on the evidence for this theory, possible mechanisms, and implications? Short answer is no. I cannot give you my take on that because I don't pay much attention to those theories. I see almost zero reason to take those theories seriously. There are retrocausal approaches to quantum mechanics where things that happen in the future affect things that happen in the past. In my way of thinking, these are all people who just can't face up to the simplicity and beauty of the many worlds approach to quantum mechanics. So they bend over backwards to have weird things happening, including signals going from the past to the future and from the future to the past. I'm not even sure that there's a coherent definition of what you mean by a signal or information there. I don't even know if these theories are well defined. But the words "I don't know" are very crucial in that sentence. Maybe they are, maybe they're great, maybe they'll turn out to be right, but I have not put any effort into understanding them, so I can't help you, Andrew. Sorry about that. Mike Gottlieb says, I thought there was a limit to the size a star could be, but it seems we keep finding ever larger stars and or black holes. Is there a limit or not? Well, it's a very different story for stars and black holes. Stars are supported hydrostatically by nuclear reactions in their core, nuclear fusion reactions. Black holes are just big regions of space where gravity is strong. They're not supported by anything at all. So for a long time, astrophysicists have thought that there is an upper limit on the size of a star, but there's some theory that goes in there, and maybe they're missing something in the theory. So there's an empirical question to be answered. What is the actual largest size? If you look at the distribution of star sizes in the Milky Way or whatever, there is absolutely, it's not random. There's a favorite size for stars to be, and there's a distribution around that size, and it doesn't go too far beyond. You do not find stars 100,000 times the mass of the sun, for example. Maybe they could exist, but just for a very tiny period of time before fragmenting into smaller stars or whatever. I really don't know, but I wouldn't be surprised if there really is a limit. As opposed to black holes, where you can always just throw more stuff in the black hole and it can get bigger and bigger. The biggest black holes that we think exist are over 1 billion times the mass of the sun. Eventually, you just run out of stuff to put in it, but other than that, there's no upper limit. T. Janssen says, if, and this is a big if, space is emergent from a quantum state and entanglement, what would this mean for defining properties of particles like location, wavelength, or energy after, during the heat death of the universe? This is a great question. it's even a great question long before the heat death of the universe. It's relatively straightforward to posit what it would mean for space to emerge from the quantum state and entanglement and the Hamiltonian and things like that. Of course, what you want is much more than that. What you want is all of physics to emerge, right? So you want fields and gauge symmetries and fermions and spin all to emerge from some underlying simple, fundamentally quantum mechanical description. I don't think we're there yet. We're thinking about it. Different people have thought about it in different ways, not just me, absolutely. But I don't think that there is a completely well understood picture of how that is supposed to happen. And then, of course, once you had quantum fields completely under control, then we know how you get particles out of quantum fields, okay? So that's basically that two-step process. From quantum field theory to particles, that part is understood. Again, look at my recent book to see exactly how that works. The previous step, fundamental quantum entanglement to quantum fields, that part is not yet understood. Okay, but then when you get to the heat death of the universe, there's a different issue going on. I would say that ideas like fields and particles, location, etc., just cease to be applicable when you're near the heat death of the universe. All of these are, you get a particle in quantum field theory when you start with space being mostly empty and then you excite it, right? You poke it, put a little bit of energy into it, and you can show that the different possible excitations have the properties of different numbers of particles with different positions and momenta and things like that. In the heat death, in the equilibrium of the universe, we don't understand it perfectly, of course, but we have every possible state in a certain superposition with certain amplitudes, with low energy states being more likely than high energy states. But there's no notion of branching and pointer states and classicality or anything like that. It becomes very, very difficult in that future heat death equilibrium quantum state to point to something and go, oh yes, there's a particle, because it's not as if it's separate from the rest of the universe, right? Like everything is kind of mushed together. It's low energy mush. It's almost nothing. It's almost completely empty space. But if we believe that there is a vacuum energy, the empty space is not exactly the Minkowski vacuum. It's a de Sitter vacuum, and it has a non-zero temperature. So if you were to probe it with little thermostats, you would see thermometers, I should say. You would see particles, but of course there isn't anything there probing it, right? Because you're in the heat death. There's no thermometers. There's no observers using it. So I just think that the honest answer to that question is that those notions don't really apply at that very, very far future time. Casey Mahone says, can you give a rough intuition for how quickly wave functions of position, for example, spread out? Say you start with a very localized particle, then its velocity is very uncertain, so does its position wave function spread out at an unpredictable rate? Or is there a standard rate at which uncertainty gradually takes over the position? There's definitely not a standard rate, but it's also not unpredictable. It is predictable. It depends on the initial conditions of the particle. So again, let's imagine we just have one particle, like you say, and it's very localized. So its velocity is very uncertain, like you say. By the way, the usual way of doing this, if you were a sophomore physics student, would be in the context of non-relativistic quantum mechanics, right? Because you've learned quantum mechanics, but only non-relativistic QM. You haven't learned quantum field theory yet. So the equation that you're using has no notion of the speed of light built into it. So in a totally real sense, the answer that you would calculate is infinitely fast. It's not that the entire wave function spreads out infinitely right away, but the edge of the wave function basically spreads out all throughout space infinitely fast, okay? That's not really what happens, because really you actually would need to take into account quantum field theory and light cones and relativity and all that stuff. And so typically, if you put exactly the situation you say, where you have very, very localized, then there will be parts of the wave function whose momenta are very, very big, right? I mean, basically, when you have a very, very localized, a wave function very, very localized in position, you don't know what the momentum is, which means that you're in a superposition of different momentum states. Some of those momentum states are very, very big. So some of them are small momentum and will spread out slowly, but other parts of that wave function are very large momentum and will spread out at essentially the speed of light, okay? In practice, of course, we don't localize things that well. So it's a very subtle thing because you don't necessarily care about the edges of the wave function. Like maybe the edges of the wave function spread out very, very quickly, but most of the wave function still spends most of its time very, very close to the center point, right? So it's a subtle question about how quickly things spread out. The important thing to note for real-world purposes is that the uncertainty principle says that delta x delta p is greater than h bar over 2. So delta x is the spread in position, delta p is the spread in momentum. And momentum is mass times velocity. So delta p is delta mv, mass times velocity. And the mass doesn't have a delta. The mass doesn't have a spread. The mass is just a fact about the kind of particle you're looking at. So delta mv is m times delta v. Okay? So this is getting somewhere, I promise. So delta x times delta p is the same as m, the mass, times delta x delta v. So if delta x delta p is greater than h bar over 2, then delta x delta v, where v is the velocity, is greater than h bar over 2m, 2 times the mass of the object. So if you have a very, very heavy object where m is very, very large, then both delta x and delta v can be very, very small. So the uncertainty principle puts a limit on delta x delta p, but the thing that we kind of notice in the world, in our big classical world, is not p, it's the velocity, it's v. So both delta x and delta v can be very, very small. And this is why, for you or for a baseball or whatever, there's no relevant quantum uncertainty in where you are. You are more or less stuck near the classical location of your center of mass. Just because your mass is very large, there's just not a lot of uncertainty there. Grouping two questions together here, Fabian Rosdalen says, do you have any favorite holiday traditions or food? And Anonymous says, what is the Carroll house like around the holidays? Do you guys decorate and get presents for the cats? Or do you bah humbug the holiday for atheistic reasons? I'm personally non-religious, but love Christmas for the sake of it. Well, we don't bah humbug the holiday for atheistic reasons. I'm not that kind of atheist that likes to bah humbug things. I think, human traditions and celebrations and ceremonies are great for whatever reasons that they historically came about. As you know, most of the things that we do to celebrate holidays in one religion or another were borrowed and adapted from other religious or pre-religious traditions that came before the religion you're actually part of. So I don't see why atheism should have anything to do with it, really. So I'm perfectly happy to celebrate holidays. We're not big decorators of the house for any purpose. We're pretty we're pretty busy, and the idea of putting up decorations and then taking them down every year, it just doesn't actually sound appealing to me. We do have somewhere on the internet I put pictures of the animatronic raven that we have for Halloween. Ravens turn out to be relevant for Baltimore, right? Because Edgar Allan Poe had his home here for a long time, and so there's a very scary 7-foot-tall animatronic that we bought when we moved into the house. And when trick-or-treaters come, they can put their foot on a little pad that starts it going, and then Lord Raven will start talking to them and waving its arms and telling them they're doomed and things like that. So that's a lot of fun. The eyes light up. But that's it. That one little animatronic is basically the entirety of our decoration for Halloween, and there's no decoration for Thanksgiving or Christmas or anything like that. In terms of holiday tradition, Christmas and New Year's, we basically lay low and just enjoy our house and good food and things like that. We used to have the Thanksgiving tradition of going to Las Vegas every Thanksgiving. And because we used to live in LA, you could just drive there, spend almost the whole week there because people would have off of universities would close, et cetera, right? But at least, spend 4 or 5 days there. And we would go and get Peking duck at Jasmine in the Bellagio, which was a wonderful way to have much better food than Thanksgiving turkey. Nowadays, we're further away from Las Vegas. So this Thanksgiving, Jennifer just cooked duck, and she cooks a very, very mean 5-spice duck recipe. So that's a wonderful holiday tradition that we're starting here in the Baltimore side of the world. Jim Murphy says, I find the existence of time to be a very peculiar aspect of physics. It seems almost too convenient that there happens to be a dimension through which events can be ordered, allowing us to have experiences of the universe and allowing for complexity to develop. This seems highly suggestive of something deeper, perhaps the anthropic principle at play. Do you get the sense that the existence of time reveals something about a deeper reality, or is it just another brute fact? Perfectly fair question, to which I don't think that modern physics provides any easy answers. It could very well just be a brute fact. I think that the way that we do physics right now, the way that we conceptualize physics right now, takes it as a brute fact. There's not a lot of deep work on why does time exist? Did it have to exist? Other than these sorts of anthropic kinds of considerations. I think that the anthropic principle is fine. The anthropic principle in the sense that if you have reality appearing as a set of many possibilities, whether they're different branches of the wave function or different parts of the cosmological multiverse, et cetera, if that is true, which maybe it is, maybe it isn't, that's an empirical question. But if that is true, then of course there's going to be some environmental selection effects. You're going to find yourself living in the part of that multiverse which is more hospitable to the existence of human life. I think that's completely unsurprising, or should be uncontroversial, but it somehow becomes controversial. However, I do think also that it can be too cheap and easy sometimes to reach for anthropic explanations of things rather than looking for deeper explanations of them. So people have thought about, what would reality be like if you had 0 time dimensions, more than 1 time dimension, things like that, and everything goes haywire. It's a very, very different universe, arguably inhospitable to the existence of life, but what do we know? I'm not necessarily sure that we would know that our universe was hospitable to the existence of life if we weren't actually living in it. So maybe there is an anthropic explanation if you think that there's some reason why there are many different versions of reality, some of which have 0 time dimensions, some of which have more than 1, etc., then the anthropic principle would help you pinpoint this one. Maybe. But I'm not aware of any version of physics that predicts the existence of those many versions. So ultimately, it might just be that we got lucky. I really don't know. I think this is, something that we're not. As we said before, you want to, in physics, ask questions that are interesting, but also ones that we can make progress on. I don't quite see right now, maybe this will change tomorrow, but I don't see right now how we can make much progress on this question. But I would like to, so if I figure out some progress, I will let you know. Thomas Prunty says, can string theory potentially shed any light on the nature of a gravitational singularity inside a black hole? Sure. Potentially. My impression is that this was one of the hopes of string theory back in the early days, and I don't really think that it's been definitively answered in any specific way. What happens is there's 2 things. One is strings are, by their nature, kind of spread out, unlike point particles. So it is very natural to hope that things that are singular and sharp in ordinary point particle theories become kind of spread out and nice and smooth in string theory. Indeed, you can make a case that this directly happens in the case of Feynman diagrams. Individual Feynman diagrams for point particle theories, which are really quantum field theories, which can be thought of in the perturbative regime, in the regime where there's only tiny excitations around the vacuum state, as collections of point particles interacting with each other. the Feynman diagrams you draw for point-like particles have sharp edges, right? They have vertices. And you can make an argument that the existence of those sharp edges helps contribute to infinities and things like that. Whereas in string theory, you have these smooth diagrams of two strings coming together and then splitting apart, maybe having holes in them or whatever, and there should be fewer singularities there, and indeed that turns out to be true. This is why string theory is a finite theory of gravity. You don't get the singularities, the infinities, that you get in ordinary quantum field theory. But the problem is that the singularity of a black hole is not in that regime where we are perturbative and weakly coupled and just a small deviation away from the vacuum state. You're near a singularity. It's a lot going on. And that turns out to be the regime in which it's very, very hard to calculate things in string theory. So the good news is that string theory sort of provides a hand-wavy optimism for resolving singularities inside black holes. But in practical terms, it doesn't seem to give you a direct route to a solution. So maybe it's there eventually, but realistic Schwarzschild or Kerr-like black holes are actually quite difficult to analyze carefully in string theory, to the best of my knowledge. Jeffrey Segal says, I enjoyed your discussion of emergence. When you discuss the measurability of emergent phenomena, could the answer be some form of the anthropic principle? Since we are emergent phenomena, we would not be present if emergent phenomena were not possible. Good. So I'm going to refer to my previous answer. Maybe, and I say maybe, by maybe I don't mean really no, but it's possible. I mean, yeah, maybe. This is absolutely possible. It's also absolutely possible that's not true. I think, again, that we should take the anthropic principle, unless you really have a completely reliable picture of what the ensemble of the multiverse looks like, which I don't think that we have. You should take the anthropic principle as a move of last resort, right? You should look for more robust explanations for things. And then maybe at the end, if all you have is this ensemble of possibilities, you can use anthropic reasoning to pick out one of them. So I don't know if we have that ensemble of possibilities or anything like that. Again, maybe it is there because of quantum mechanics or inflation or string theory or whatever, but I don't think that we have a very good grasp on it. So I think that instead, the obvious thing to do in the short term, the near term, is to think about the conditions under which emergence arises at all as a general theory. And then we'll try to figure out, are those conditions robust? Are they generic? Are they special and fine-tuned, et cetera? We don't know the answer to any of those things. And I think making progress there will help us with questions like this. Brett Slog says, I'm trying to reconcile the idea that Laplace's demon could accurately describe all the branches of the wave function, if equipped with the initial state of the wave function and the Schrödinger equation, with the fact that gravity is not yet incorporated into the standard model. I accept that gravity is too weak to matter at small scales, but clearly it does matter even at our everyday level. Wouldn't Laplace's demon make horribly inaccurate predictions about the state of the macroscopic universe if equipped only with the Schrödinger equation? Well, I think that technically what Laplace's demon is supposed to know is the current state of the universe in whatever theory correctly describes the universe, plus the complete laws of physics in whatever theory describes the complete laws of physics. So if that's quantum mechanics in its standard form, if it turns out that quantum mechanics in its currently understood formulation is basically the framework that is exactly right as far as the universe is concerned, then it would be the current wave function and the Schrödinger equation. But the Schrödinger equation is a very general thing. It's not just the non-relativistic Schrödinger equation. The Schrödinger equation says h psi equals I d by dt psi, as the tattoo question before referred to. That means the Hamiltonian of the universe tells you how quickly the quantum state is evolving. Clearly, Laplace's demon is going to need to have a version of the Schrödinger equation that includes everything, including gravity. So it's certainly not that we're imagining Laplace's demon can ignore gravity. It's just that we're imagining gravity has to be included in the correct version of the laws of physics that Laplace's demon actually uses. JMS 547 says, in your intro to your first podcast after the U.S. election, the one on emergence, you said that for you at least, part of the fight against the erosion of democracy is to not only keep engaged in the political discussion, but also keep on pursuing your interests in your quest to better understand the universe. While I wholly agree that that is reasonable for you, I don't know whether that's enough for me. I'm an early career researcher in applied mathematics and physics. At this juncture in history, I feel that any contributions I might make to physics are too small, and the need to fight the tidal wave of authoritarianism to resist the collapse of liberal democracy is too urgent. Have you any advice on how an applied mathematician with some training in complexity science might use their training to fight for the restoration of democracy, decency, and the rule of law? Well, I think it's a great question. As I hope I made clear, I'm extremely pluralistic about the ways in which one can adapt to and confront and try to improve on the current state of the world. Okay, some of them will be direct, saying threats to democracy are the most important thing, or poverty is the most important thing, or future pandemics are the most important thing, whatever it might be, and then literally devoting your life to trying to make that particular situation better. That's entirely reasonable, realistic, and it's a good thing that some non-trivial number of people do that. Likewise, I don't think everyone should do that, as important as those things are, because that's sort of sacrificing the life we're trying to preserve for the sake of trying to preserve it. We need to keep a variety of things going. Even if everyone is well-intentioned and wants to make things better, it's okay that some people spend some fraction of their time doing that and some fraction of their time doing other things, ordinary, flourishing human life things as well. Having said that, JMS 547, I think it's good that you are so concerned about these kinds of issues and want to try to do better. But your question is a tough one. How can an applied mathematician use your training to fight for the restoration of democracy? It might be that the best, most effective way to fight for the restoration of democracy doesn't actually end up using your training. I don't know. It's not perfectly clear to me how that directly applies. One of the reasons why I want to, and I promise I will eventually, write a book called The Physics of Democracy is because I think that is some tiny way in which my own training and interests can substantively contribute to strengthening democracy and things like that. But if one is at all honest, it is extremely indirect and slight compared to, directly being there in the trenches, trying to get people to vote or to improve our information ecosystem, as the previous question referred to. I mean, maybe that's an answer. And I'm just thinking out loud because I have not thought about this a lot. There was a previous question on, what can we do about the future in which it looks like the information ecosystem is just deteriorating because of AI and bots and misinformation and things like that. Maybe that's a way. Maybe that's a field, a subject, a problem in which applied math, some training complexity science can help. Think about the dynamics of information flows at a practical level, not just at a very theoretical level, or even at a theoretical level for that matter. Think about why people, engage with people who have done the empirical work on the psychology and political science side of things. Think about how we can organize this complex system, which is our information ecosystem, so that it better aligns with what we wanted to do, better helps people be informed. Maybe, or something like that, right? I mean, there's certainly academic areas one can study in. Study the collapse of societies. Study, do the political version of what Don Farmer was talking about with complexity economics. Do complexity political science, But that's, you have to confess, like there's an academic version of that and there's a more real world version of that. And the academic version is more broad and intellectually deep, and the real world version of it is we got to solve this problem right now. And they're both worth doing in different ways. So I think there are ways, but I think at the end of the day, you might have to confront the fact that using your training is not necessarily compatible with fighting the good fight in the best possible way. I don't know. Maybe it is, but that's absolutely a possibility. Justin Wolcott says, election discussions often frame voters as a fixed pool, with candidates competing to sway a shared middle ground, suggesting that a centrist candidate could draw support from both sides. Results are often interpreted through this lens. In the 2024 U.S. presidential election, Donald Trump beat Kamala Harris in the popular vote by 10 million. However, Trump's vote count remained the same as in 2020. Harris lost 10 million votes compared to Biden's 2020 tally. The story isn't about Trump flipping Biden voters. It's about Biden voters not showing up. Politicians may prioritize energizing. Sorry, I missed a sentence. This highlights how voter turnout often outweighs voter conversion. Politicians may prioritize energizing their noisy activist fringes with bold, attention-grabbing rhetoric rather than focusing on bridging divides. Well, yeah. I mean, I think this is actually pretty well known. I do think that you need both. Just to correct one misimpression, it's absolutely not true that Donald Trump beat Kamala Harris by 10 million votes. It's less than 3 million votes now. The votes take time to trickle in. It's actually quite a close race in the popular vote. It's one of the closest historically that we've ever had. And when you say the story isn't about Trump flipping Biden voters, it's about Biden voters not showing up. Yes, to some extent that is true, but it's a little bit more complicated than that as well. There are people who voted for Trump in 2020, voted for Kamala Harris this year, vice versa, voted for Biden 2020, voted for Trump this year. It's just complicated. I do think that every political expert knows the importance of turnout, the importance of enthusiasm in the base, getting people out to vote, etc. The question is how to do it. And also, there's virtue in getting people who are low information voters to sort of lean over to your side. There's the number of stories that have come through since the election of people voting one way or the other, and the reasons they give for voting that way are kind of horrifying, just in an intellectual level. Some large number. Anyway, there was one, maybe it's just an anecdote, so I don't know whether this is true or not, but there was a claim that, in the pandemic in 2020, the government very correctly gave out stimulus checks, right? Checks would arrive in the mail to people. And Donald Trump insisted that his signature be on those stimulus checks. And previous versions of checks like this had not been personally signed by the president. Obviously, he didn't sign them himself, but there was an image printed of his signature. And apparently some non-trivial number of people thought that was his own money, that Donald Trump was giving his money to people during the pandemic. Needless to say, that was not true, but people think that. And those people are not necessarily polarized. They're not necessarily the strongly Republican or strongly Democratic leaners. They're people in between who just don't pay attention to politics. So I think that there's a lot going on. You can't just say, I have the secret sauce to make things better. The Harris campaign, it's absolutely true that the turnout killed her, right? The turnout absolutely did not do a good job. But if you look at the details, they did much, much better in the swing states where it's important to do well relative to how well they did in the solid states, red or blue. So in terms of strategy, there's an argument to be made they did the best they could given the fundamentals and the situation that the race was in. That's always going to be debated because it's easy to invent stories after the fact, and it's hard to really understand what different choices would have done. But I do think that the fact that you got to get the base fired up and get good turnout is well understood among political professionals. Red Antonov says, in a recent appearance on Why This Universe, you discussed a result from DESI, D-E-S-I, the dark energy spectroscopic instrument, in favor of dark energy varying over time, albeit at 3 sigma currently. If the statistical significance rises to the threshold of a discovery, how would it affect your thinking about the possibility that space-time is an emergent phenomenon? As a follow-up to your solo podcast on emergence, which category would you place space-time in? The emergence of space-time story, number one, to give you a direct answer to your question, I think it's fine no matter what the cosmological constant is. And number two, into which category, it's type 1 emergence. It's pretty straightforward, local to local, at least when gravity is relatively weak, right? When gravity is strong, if you're near a black hole or something like that, non-local effects start kicking in and the story becomes complicated. That's exactly where we don't understand it. So I don't think we can say very much. But I don't think the emergence of space-time is an especially tricky or subtle example of how emergence works. About the cosmological constant versus dynamical dark energy. So There is a tiny repercussion. I think that space-time is emergent no matter what. I think that we have lots of reason to think that quantum mechanics is more fundamental than general relativity. Quantizing general relativity straightforwardly doesn't work. It's better to think of gravity and space-time as being emergent from quantum mechanics. None of those words had anything to do with dark energy or the cosmological constant, okay? But the details do. There is an important implication if the dark energy is constant, that is to say, if it is a cosmological constant, then the future of the universe looks like what we call de Sitter space, an empty universe with nothing but vacuum energy in it. And that's a very interesting space-time. It has horizons. There is a de Sitter horizon, which is almost the size of the cosmological horizon now. It's a little bit bigger than that. And that means the universe, the observable universe, always remains finite in size. And it also, because there's a horizon, we get effects much like Hawking radiation, except that we are inside the horizon rather than outside the horizon. So de Sitter space has a temperature, just like a black hole does. And most importantly, it has a finite dimensional Hilbert space, to you Hilbert space fans out there. So the details of how to get emergent spacetime in finite dimensional Hilbert space might very well be importantly different than the details of how to do it in an infinite dimensional Hilbert space. If the dark energy is time dependent, if the dark energy is slowly decaying over time, then it's completely plausible that eventually it will go to zero, and the future of the universe doesn't look like de Sitter space, but rather like Minkowski space, like flat, empty space with nothing going on. In that case, there is no horizon around us, and as far as we can tell, the dimensionality of the Hilbert space of the observable universe is infinite dimensional. So then all sorts of tricky mathematical difficulties rear their ugly heads, and the details will be different. I don't think the fundamental lesson that space-time is emergent changes, but I do think that the specific technical implementations might be affected a lot in ways that I really don't understand. Physics Kitten says, in Something Deeply Hidden, you argue that the most austere, elegant interpretation of the wave function of the universe, evolving according to Schrödinger's equation, is that many worlds are generated when a macroscopic object becomes entangled with something in a superposition of states. But I suppose I challenge two assumptions. First, why do we think that the wave function is real as opposed to just a mathematical construct to generate probabilities? And second, just because Schrödinger's equation generally describes how a quantum system evolves with time, who says there isn't another equation that produces a single deterministic result with the correct probability when decoherence occurs? Who is to say that the two formulas are less austere than the countless numbers of separate worlds? Well, I'm going to go backwards. For the last question, the number of worlds is entirely irrelevant, right? It's never the number of worlds that counts when you're talking about the simplicity of a system. Just like the number of numbers does not really matter if you're talking about the simplicity of a numerical collection of things. What matters is the ideas, the concepts, the formulas, the equations that generate what happens. The integers are not more austere than the real numbers just because there's fewer of them. The odd numbers are not more austere than the integers, etc. Okay, so the number of worlds is completely irrelevant. It's the concepts underlying the theory that make it simple and austere or not. As to your specific questions, why we think the wave function is real is because it interferes, right? Because there's quantum interference in the double slit experiment, or for that matter, in any particle physics scattering experiment. The wave function can be negative or positive. It can be imaginary, either positive or negative. And those values of the wave function add together constructively or destructively to give the final answer. That is something that is very characteristic of a real thing. If you're not real, if you don't really exist, how do you interfere with yourself? And how does that interference matter? When the electron goes through the double slits, its behavior is exactly that of a real honest-to-goodness wave going up and down. That's the evidence that the wave function is real. And there's more sophisticated versions of that, but that's the basic idea. In terms of who says there isn't another equation that produces a single deterministic result with the correct probability, well, first, I would wonder about the word deterministic and then the phrase with the correct probability. I'm not sure what that means. Deterministic results don't have probabilities in them. But second, yeah, if you can find that, then great. Good for you. But you would have to find it. It's easy to say, if I had a better theory, wouldn't it be better? Yeah, okay, maybe. find a better theory. I encourage you absolutely to do that. Humberto Nani says, how is it that water evaporates from my towel, which is at room temperature? How do the water molecules gain enough kinetic energy without a source of heat that makes them boil? Well, this is a very good question, and I think that, I don't know if this is too slick, but I think that the best intuition for this is to think of entropy instead of temperature. I mean, there's one answer to your question, which is just that you don't need to literally boil the water. You just need water molecules to, one at a time, have enough energy to escape the towel, right? So it's not that every single water molecule is turning into water vapor. It's just that one at a time, the molecules escape into the air. And there's a distribution of kinetic energies, right? They're not all exactly the same kinetic energy. So even at room temperature, some of those molecules are going to be moving pretty quickly and will be able to escape. But the more general principle involves entropy, which is to say, which configuration has higher entropy? The water scattered throughout the air or the water sticking to the towel? And when you think of it that way, it's pretty clear that the water distributed throughout the air has higher entropy, okay? So if it can get there, the system is going to go there. Of course, the molecules in the towel scattered throughout the room also have higher entropy, but they don't do that because they're held together by very strong individual molecular forces in the towel. So you can't get there from that initial starting point. But the water is much more weakly coupled to the towel. Water is a liquid, it's spread thinly, etc. So gradually the water at the surface of the water droplets or the fibers of the towel will indeed just increase their entropy over time. You don't even need the towel, right? A cup of water will eventually evaporate into the air, ultimately because it's a higher entropy configuration. Miran Mizrahi says, in your quantum mereology algorithm, this refers to a paper I wrote with Ashmeet Singh a few years ago, you say that for each factorization, you find a pointer observable that commutes with the interaction Hamiltonian. Presumably this is to ensure that a localized state remains robust. Then you start with an unentangled state of one of the pointer eigenstates. Then you minimize the entropy growth rate. So am I right in interpreting this as the right factorization is one where if I start with a localized state, I am most likely to remain in one? If so, isn't this circular reasoning because I am starting in a localized macroscopic state and the whole point is to show that one emerges? Unsurprisingly, I'm going to say no, it is not circular reasoning. The whole point is not to show that a localized macroscopic state emerges. The whole point is to show that it is robust once it emerges. So if you start, Schrödinger's cat is the classic example, okay? The whole point of Schrödinger's cat in the superposition of awake and asleep is that is not robust. That is not macroscopically stable. Even a little bit of interaction with the photons and the air molecules around it will get entangled, and then you will branch into two different branches. But then, crucially, and people don't talk about this as much, but it's very important, once that happens, once you have a branch where the cat is either awake or asleep, you don't keep entangling. The cat is just there. The cat is just there in its macroscopic state. This is a feature of big macroscopic classical-looking pointer states, is that they don't continually become more and more entangled with their environment. So the point of quantum mereology has to do with, it absolutely does take as input the empirical fact that the early universe started with low entropy. There is an arrow of time here. Every discussion of the Everettian version of quantum mechanics involves the need for an arrow of time, in particular a low entropy past boundary condition. So you have to imagine that somehow there are unentangled states in the universe, and then you're arguing that they will stay that way. At least they will stay that way for a very long time. Not forever, as we talked about before. Eventually you'll reach the heat death of the universe and everything will be smeared out. Brendan Hall says, as a fellow book addict, I need to know if you are still buying books all the time and will you ever finish even half of them? Certainly the number of books I will finish is far less than half of the ones I acquire. Two things happen when you become a podcast host. One is you have some motivation for reading certain books, namely the ones that your podcast guests have written. Indeed, this was a big motivation for starting the podcast in the first place, to motivate myself to actually read all these cool books. And, maybe you don't read them as thoroughly as you should because next week there's another podcast to do. But I absolutely have been doing reading of things like that, and it's a lot of fun to do that. The other thing that happens is if your podcast becomes successful, people just send you books whether you like it or not. And I feel very guilty about that. When I was young and poor, I would just spend hours in the bookstore gazing longingly at all those books and trying to scrape up money to buy them. And now literally people send me books I don't want, in addition to sending me books that I do want as well. So I try to figure out clever ways to give them away. There's like this little box outside a restaurant a few blocks away from our house that I pass by on the way to my walk to the office, which is sort of like one of those little lending libraries, just like an open box, take a book, leave a book kind of thing. So I've left a lot of books in there. I've never taken a book from there. I have more than enough books. Let's just put it that way. I'm a big believer. There's a wonderful essay by Umberto Eco about the need to have a library, the joy of having a library, which is to say, you shouldn't imagine that you only buy books that you're instantly going to read. It's entirely okay to have books and have them on your shelves for years and never read them, with the possibility that maybe you will read them or at least just refer to them in the future. And honestly, that happens all the time. I very, very often take down a book that I bought years ago, haven't read, and have a need to look at right now. So I think that's fine. Christopher Burke says, where do you draw the line between hope and delusion? Is there a difference? Is hope a fundamentally bad thing with normal people working around that with delusion? I don't know if there's a line to draw between those. Maybe the difference is just delusion is a conviction, whereas hope is an aspiration, right? Delusion would be if you are convinced that something is going to happen and it's really not. That's a delusion. Hope is to say, look, I'm not sure what the probabilities are, but I think there's a non-zero probability for this. I'm going to hope that it happens. That's a desire. It's not a conviction. And I think that both are, there's reasons to have hope. Hopefully there's no reasons to have delusions. I do think that people should be more or less realistic about the prospects for different things coming to pass. But there's absolutely reasons to wish for certain things to come to pass rather than others, and I think that's what hope is all about. It is okay to say, okay, a certain outcome is unlikely, but I'm going to hope that it's going to happen. I'm going to work toward making it happen. Hope is an important psychological aspect of motivating yourself to make the world a better place. David Maxwell says, in the June 2024 episode, you joked that after dedicating the first 3 books of your latest series to your wife and your 2 cats, that your additional stray cat would get the dedication for a hypothetical 4th book. If you were compelled to write a 4th book in that series now, what would it be about? I honestly don't know, actually. I think that the obvious thing, well, let's put it this way. I have run out of things I'm an expert on in the first 3 books. If one kept to the spirit of the first 3 books, which is that we are talking about areas of science that are more or less established, right? That are not just speculations, that are things that we're going to still believe are more or less accurate to their domain of applicability in the next 500 years, then there's plenty out there that is interesting science, but not that I'm expert enough to write this book about. Writing a book like this involves, exactly because it's established science, plenty of people could write the book, but you do bring your own personal spin to it by understanding the material deeply. If you understand it really well, it's necessary to understand it really well in order to pick out the parts that are truly essential and try to explain them. So I could write a book about life, right, about biology and evolution and things like that. These things I think are fascinating, but I'm nowhere near enough of an expert about that to really pull it off in a way to make it a good book in the spirit of the Biggest Ideas volumes. The other possibility would just be to throw out the idea that we're only writing about well-established physics and make the 4th book about completely speculative stuff. But then it's just a grab bag of different speculations and things like that. So honestly, I'm not motivated to write a 4th book. As much as Puck, our little kitty cat, who is our newly adopted stray, deserves a book of his own, he's going to have to wait for some completely different excuse. Pete Faulkner says, I've often heard Hawking radiation explained through the popular visualization of virtual particle pairs appearing near a black hole's horizon, where the negative energy particle falls in while the positive energy particle escapes as radiation. causing the black hole to lose mass and eventually evaporate. What troubles me about this explanation is that it seems to assume that negative energy particles always fall in. If this particle creation process was random, wouldn't we see both negative and positive energy particles fall in with equal probability, resulting in no net mass loss? This is a great question, but there is a very definite answer to it. It turns out that energy is tricky in general relativity. You're talking about the energy of a particle. What does that mean? Okay, I mean, you should instantly worry that there's something fishy about the very idea of the energy of a particle. If the particle is massive, like if it's an electron-positron pair that is produced as Hawking radiation, then there's a kinetic energy associated with the particle that could be anything depending on how you're moving with respect to it, right? That's even true for massless particles. There's still a kinetic energy, a momentum that's going to depend on your rest frame. You can redshift or blue shift the particle. So what do you mean by the energy of the particle? And there is an answer to that. The answer is that in the black hole space-time, there is a symmetry. There's a symmetry of time, translation, and variance. There's a symmetry of the direction you move in space-time so that all of the space-time remains the same around you, okay? That's a very simple notion in flat space-time with no black hole in it. Everything just moves forward in time. That's time translation. In the presence of the black hole, it's a trickier thing. The time translation symmetry is a bit subtle, and you have to be very, very specific about what you mean. But that notion of time translation and variance is used when you define the energy, okay? It's the energy of the particle in the reference frame defined by this particular, basically the rest frame of the black hole, okay? And also, it is measured with respect to some observer. Some particular observer is telling you what the energy is. And in this case, in the case of the black hole, it's an observer outside the black hole, maybe infinitely far away, but that's just a detail. It doesn't have to be infinitely far away. But outside the black hole, stationary observer, with respect to them, we're measuring the energy, okay? And then the point is, if instead you're just falling through the event horizon, both of the particles going in and going out, to you, have positive energy. To themselves, they have positive energy. But through the mysteries of curved spacetime and general relativity, to the external observer, you can have ingoing particles with negative energy. You can't have outgoing particles with negative energy. That's just not possible. Particles have positive energy in their rest frame, and outside the event horizon, that's going to mean they have positive energy with respect to the observer far away. But the ingoing particle, the one that passes through the event horizon, is just a feature of general relativity long before you get to Hawking radiation and all that fanciness. It is possible for a particle whose energy is measured from the point of view of an external observer going into the black hole to have a negative energy. So it is not that a negative energy particle goes in by chance and a positive energy particle goes out. It's that two particles appear, one going in and one going out, and from the point of view of an external observer, the ingoing one will always look like it has negative energy. The outgoing one looks like it has positive energy. Obviously, there's a lot of math underlying that explanation that you just have to take on trust, but that is the way it works out. It's not a cheat in any way. UTE, or UTE, I don't know, says economic models for depopulating post-industrial societies. At some point this century, all nations will go through a decline in population as they industrialize, even sub-Saharan Africa. Technology can help with production, but what about the consumption side? Can living longer and more productive lives be the answer? I don't know what the answer is. As I've said on previous podcasts, this is so incredibly low on my list of worries that I just kind of have to giggle about it a little bit. We're nowhere near population going down yet. Maybe someday in the future, after I'm dead, the population of the Earth will start to go down. Not really very worried about that. The population of the Earth is pretty big. It's billions of people, okay? How in the world, I don't know, where do people get the idea of what the right population should be? It seems to me that the current population is good enough. Seems to me we were doing well with a smaller population than we have right now. Of course, if your worry is that ultimately, no one has kids anymore and the human race just extinguishes itself from a lack of reproduction, I suppose that's a worry, but it seems to me that is a very, very, very far off worry and kind of unrealistic. I think that there's a lot of changes going on, and the total population is just a very crude and not that interesting measure of human life on Earth. I always go back to the podcast with Joe Walston very early on in the podcast history about urbanization and conservation. And the idea that the human race, it's the much more important thing than the population growth is where the population is living. Increasingly, it's living in cities. And that turns out to be a good thing for the planet. It means that we can devote more and more land on the earth to things that are not human beings, stomping all over the place. Part of it can be for growing food and things like that, but part of it can just be wilderness. And we can actually live successfully in harmony with the rest of the earth if we have most human beings in cities and most of the earth be doing its own thing. Okay, that is a plausible future equilibrium for the world. We're nowhere near it happening right now, but I think that you have to take many, many things into consideration before you begin to worry about depopulation. So it's just not high on my list of things to care about. If you're like very short-term worried about the population of a particular country just because you need a workforce, okay, then allow for immigration. That is clearly the answer that has traditionally worked, and I think it should work going forward as well. Paul Saldera says, you've talked a lot recently about emergence with regard to physics, and you've often talked a lot about AI. Your current stance on AI is that it doesn't reason. Do you think that the ability to reason like a human or an animal could be an emergent trait of LLMs once they get large enough? Anything's possible. It could be. I mean, I think that's absolutely is part of the hope, right, of the LLM enthusiasts, is that even though what you're training it to do is just next token prediction or whatever, if predicting on the basis of a sufficiently large data set and being sufficiently subtle about its predictions, then what it will end up doing amounts to reasoning, even if the details of how information flows through the neural network do not match on to the details of how information flows through a human brain. If it reasons, if it comes up with exactly the same answers under a reasonable set of input parameters as a human brain would come up with, then that is emergent reasoning. Again, I think there's plenty of reasons to think that's not going to happen for LLMs, but I could be wrong, as I've always said. So that is something people are trying to get to happen. There was a very good paper that I read by Schaefer et al. Recently, because people have claimed that this kind of emergent reasoning really does happen, and they have plots of, as a function of the size of the LLM, you test it on different measures, and you see that it's like not doing well, not doing well, not doing well, and then it sort of dramatically improves its performance. Turns out that this paper argues that that's kind of an illusion. It completely depends on what criterion you're using to judge success on the tests, and you can slightly tweak your criterion for success on the tests, and this sudden change goes away, and the location of the sudden change is entirely dependent on what precise test you do, which is not what you would expect from truly emergent reasoning. So I continue to think, along with many other people, that the future for more general reasoning in artificial intelligence is completely plausible, but will not be LLM based. Darren Ho says, imagine hypothetically we could measure every particle in the universe, thereby collapsing every particle's wave function to have a definite position. Would the universe cease to be quantum? Can a particle be re-quantized? Well, the particle is never unquantized. When wave functions collapse, they collapse to other wave functions. It's still a wave function, both before and after the collapse. It's just the wave function becomes localized. And as we talked a little bit about before with the uncertainty principle, if you localize things very, very, very well, they instantly spread apart, right? Delta X is very, very small because you've localized the particle very well. Therefore, delta P is large. Therefore, different parts of the wave function correspond to small momentum pieces and large momentum pieces, which means that it spreads out very, very quickly. So there's no sense in which the universe would just suddenly become classical looking or anything like that. I'm not going to, should I read this out loud? J4ND3R53N, which I think is Janderson, J. Anderson, with a combination of letters and numbers, says, in a recent podcast, you talked very interestingly about emergence, and it reminded me of something I learned all too long ago. Well, two things. One is that in set or group theory, where we define an equivalence relation on a universe of sets and then use it to bundle up the things that are equivalent so we can concentrate on the remaining structure. But this looks and feels a lot like what happens in category theory with a forgetful functor. So going from a detailed theory such as statistical mechanics to a less detailed one like thermodynamics, we filter out a lot of details because to our macroscopic view, they're all the same. We apply a forgetful functor, which carries over the interesting structure but filters out unimportant details. Perhaps this kind of abstraction process is in essence what emergence is about. I don't think so. I mean, I think that there's a sort of family resemblance, but I think ultimately different things are going on. For those of you who don't know about forgetful functors in category theory, which might be most of you, you have in category theory, you don't just deal with groups or fields or rings or sets or these different kinds of structures that you pick at that you look at sort of one at a time in ordinary math. You can look at all of them. You can, you talk about relationships between sets and groups and fields or whatever. And a forgetful functor just says, I have some object. Let's say it's a group, okay? The group SU3, the group of 3x3 special unitary matrices. And that is an 8-dimensional manifold, if you think about it that way. And so let's take that group, but then let's forget that it's a group. Just treat it as an 8-dimensional topological space. Okay, that's a forgetful functor. You can do that. That's a little bit different than a coarse graining map. And a coarse graining map is a different kind of thing. In a forgetful functor, you're forgetting some of the structure, but keeping other parts of the structure. In a coarse graining map, you might not keep any of the structure at all. It can be a much more subtle thing. It's really a map between sets and sets almost exclusively. And so it's not quite like you're forgetting or ignoring some mathematical structure. There's clearly, like I said, a resemblance. Maybe there's a relationship. Maybe that kind of relationship can be useful in certain special circumstances. But I don't think there's any sense in which emergence is just that. It's a little bit more subtle. Anders says, I hope we get a puck update, a puck date. Many cats get very concerned whether humans use the shower or the bath. Do Ariel and Caliban care? All good questions. Yes, I should give a puck update. I forget when the last puck update was, so forgive me if you've heard this before. I'm up here in the Mindscape World Headquarters recording studio, and Puck he's very close by. I don't actually see him right now. I think he's hidden under his blanket. But Puck is doing great overall. There was super fast progress in the first few weeks. We brought him in September. And so it's just been a couple months, and there was super fast progress. Progress is now slower but still steady. So, when we first got Puck, for a year he was an outdoor cat exclusively, and he would, the very first time we met him, he ate out of my hand because he was starving and he wanted to eat. But since then, he had no interest in being close to human beings. Like, he could be fine if he were 5 to 10 feet away from you. He was chill. He didn't run away when he saw human beings. He was curious and he would come to visit, but he would want to keep his distance. And we brought him in, and we thought he would have a certain amount of agita just being inside. Maybe he would meow or try to get out or whatever. Zero interest in that. He loves being inside. He loves being in a warm, comfortable environment with blankets and food and the whole bit. So he instantly became very indoor cat-like, and it was really a matter of socialization, right? Is he going to get to know human beings? And so one night, we're just sitting there. Jennifer and I are up in the room with Puck. He's sequestered off from the other cats. That's the big barrier we will eventually have to come to at some point. He needs to socialize with Ariel and Caliban and mix with them. We haven't even done that yet. We're trying to get him happy with human beings first. So we were up in the room with Puck and we were watching TV, and suddenly out of nowhere, he just comes and starts rubbing up against our legs. This was a huge improvement, he had been here a few weeks and he didn't like being touched or being approached, but suddenly he was coming up to us. And so it started with just rubbing up against our legs and we were sitting there, and then gradually we would lean a hand down and he would sniff it and he would sort of think about it. And then we started giving him scritches, and he realized, oh my God, this is the best, scritches. And so now, two things. One is he just demands the scritches. As soon as you come in to the room, he's like walking over to you and rubbing up against you and wanting those scritches. He really loves them. So much so that when you leave, he like attacks. He like puts his paws around you. He doesn't want you to leave. It's very, very adorable. And the other breakthrough that happened a little while after that was he discovered that he can climb onto your lap. And so again, this happened. We let him do it. We didn't sort of coax him into doing it. It's all Puck's own choices. And then he found that he could sit on a lap, and that was nice. And he could get a little more scritches there when he's on the lap. And now, again, he absolutely demands it. Like, if you come into the room and sit on the couch, he will be in your lap within 30 seconds, and he will sit there for hours. He's perfectly happy. So I can't come up here if I need to do work. Like, it used to be good. You could do work in the room with Puck because you would have your computer and he would be on his chair or whatever. Everything is good. But now he's on your lap all the time. Now, there's still some spiciness there, as Jennifer says, like, because you can see it's fascinating. The kitty brain has multiple components to it, right? So he will absolutely come up to you and rub up against you, and he'll be purring and meowing, which feral cats generally don't do. So that's another big leap forward. And then he'll like suddenly a different part of his brain will kick in, and he'll go, "Oh wait, you might be dangerous," and he'll sort of turn around, and if you're foolish enough to like leave your hand hanging down there, he will start batting at your hand with his claws, right? And then he'll instantly start rubbing up against you and purring again and wanting more scritches. So it's not like he's actually in any coherent way upset or mad with you. It's absolutely that there's different parts of his brain that are sending his body different signals. So we're trying to sort of smooth out those rough edges before we introduce him to the rest of the world and to the cat world. But the short answer is he's super duper happy. He's very affectionate and loving. And once we get him, we're trying our best to get him calmed down and used to being around people and other kittens and things like that, I think it will all be good. In terms of the shower and bath, longtime Mindscape listeners know that Caliban couldn't care less. Ariel, back in the day, she loved getting showers. When we were living in Los Angeles, she had a regular daily routine. She didn't care whether we were in the shower, but after we were done with the shower or before we used it in the morning, she would demand a shower. What that meant was just turning on a very slow drip of drops of water from the shower head, and she would climb into the shower and just sit there and let the drips fall on her and then lick the water off. Okay, that was her routine. She liked that. She did it a couple times when we moved to the little apartment in Baltimore, but now that we're in the house in Baltimore, she doesn't do that anymore. So I don't know. We've tried. She has explored the shower. She's looked around, but she goes, "No, this is not what I'm used to. This is not my shower. I do not want to get drips on me anymore." That's fine. She has other routines. All cats are very routine based, so they now have different customs or things they expect to happen at different times of the day. As long as those things happen, they're cool. David says, in weak emergence, the higher theory can be derived in principle from the lower, though it might be hard. In strong emergence, it can't, implying that the lower level theory is incomplete. Is there a third type in the middle in which weak emergent is not just hard to compute, but exponentially hard in some sense that computer science would view as impossible? Does Mark Bedell's computational conception of weak emergence still have meaning if the simulation can never complete? Yeah, I absolutely think there is. This is something we talked about a little bit in the paper with the tooth parola. That when you say compute emergence, that you got to be a little bit more specific. Like, what exactly is being computed? Emergence is a relationship between theories. So are you saying you're discovering the emergence map, or are you saying you're calculating which microstate goes to which macrostate given some emergence map? In the latter case, I think that it can be a very hard problem. Like, okay, here's a microstate. What macrostate does it correspond to? I don't think it's super hard, but I think there's levels of difficulty there. There will be in general. And so, yes, and this is why some people think of emergence as something a little mystical, because sometimes it's easy right? Thermodynamics can be directly derived from underlying atomic theory or something like that. Sometimes it's much less obvious, and so people think, well, if it's not obvious, it must be mystical or something like that. And I don't think that's the right way to think. Mark Robinson says, it's a really interesting show with Eddie Pross, especially around the importance of persistence in evolution. We humans have the ability to increase complexity on a global scale, but an AGI without our limitations on scale or lifespan might be able to increase complexity on a cosmological scale over billions of years. Do you think a teleonomic process might be cognition plus motivation to persist equals increased complexity and increased entropic efficiency? Two things there. Complexity and increased entropic efficiency are not really the same thing. There's no law of nature that says that entropy has to increase as fast as possible. At least there's not any law that I know of. There's a law that says entropy increases rather than decreases in closed systems, but that law tells us nothing about how fast it does it. Sometimes we informally gesture towards something like, oh, that allows entropy to increase faster, so that's why it happens. But that's not actually reflecting any law of nature. That's just kind of a amusing human gloss that we put on it. Again, as far as I know, maybe there's circumstances under which there is such a law that I just don't know about. But okay, putting that aside, increased complexity is the trickier thing. Complexity won't increase forever. It can't be a law of nature that complexity will always increase, because eventually it will decrease, because the heat death of the universe ends up in a very, very simple state, okay? So I think that you need to be a little bit more subtle here. I don't know whether the general ideas of what you're suggesting are on the right track or not, but I would advocate that if you're thinking along these lines, you just have to roll up your sleeves, do the dirty work, and think about different circumstances, different definitions, how things would play out, what the limitations are, what the resources are, and so on. Bruno Frank Goularte says, I completed my doctorate in continuum mechanics, which often feels like the antithesis of quantum mechanics, my current area of interest. Continuum mechanics is deeply rooted in classical physics and heavily relies on integral and differential calculus. Sometimes I wonder if we need to reinvent a mathematical formalism to capture the depth of quantum physics as effectively as Newton's differential equations did for classical physics. So my question is, are we constrained by our current mathematical and numerical tools in expressing the complexities of quantum physics? Well, I don't know. I mean, it's basically equivalent to saying, is there a better mathematical or numerical tool to understand quantum physics that we don't yet know about? And the answer, almost by construction, is I don't really know. I don't think, personally, that mathematical lack of sophistication is what is keeping us from understanding quantum mechanics. I don't think quantum mechanics is that hard to understand. I think people are not doing it, but I think that, my personal way of understanding it is on the right track. Again, lots of people think this, even though their personal ways of understanding quantum mechanics are entirely incompatible with each other. So when I say that physicists don't understand quantum mechanics, I always try to be very, very explicit that what I mean is they don't agree on the understanding of quantum mechanics. I think it's a mistake to think that there's any deep barrier to understanding quantum mechanics because it's just too hard. It's really not that hard. It's just a matter of coming to grips with what it says and accepting what it says, and then trying to focus on answering the deep questions, the hard problems that are faced by what it says. Having said that, maybe the right answer for doing that is a better mathematical set of tools, but I don't see exactly what they would be, so I'm not really in any position to comment on that. Ernst Nathorst Buzz says, listening to the episode about emergence, I have a question. You and others use words such as appear or manifest when describing emergence. This rubs me the wrong way. That wording sounds to me like it implies that a higher emergent level, such as temperature, molecule, or even consciousness, is something that actually exists, independent of us humans observing and having theories about it. Is that the way you understand it? To me, it intuitively rather seems that another being could potentially connect with existence without sorting reality into emergent phenomena. That theoretically it would be possible to exist and only see and interact with the lowest levels of reality. And that the idea of emergence is just an effect of how human brains happen to be constructed, of how we sort and store information. Your thoughts on this? Yes, my thoughts on this are that is not correct. that two things. Number one, the existence of the emergent phenomena is a real pattern, as we discussed way back in the AMA. It's objectively there, okay? There are certain ways to group up the world into emergent higher level things that work and give you causally useful explanatory theories at the higher level, and most ways would not. So there is something special about the emergent patterns that is completely independent of anyone perceiving them or using them. The second thing is that given the laws of physics, there are limitations on what can be observed about systems. You cannot actually imagine in the real world a being that is able to measure the position and velocity of every atom or molecule of air in the room I'm in right now. There aren't enough photons to do it. There isn't the ability to sort of measure all of those photons at any rate, even if you are very, very good at it. This is why robots tend to observe more or less the same world that we do, even though their sensory organs are completely designed by human beings. There is, just like there is a naturalness, a reality to the groups of things that make up the higher level emergent things, there is also a naturalness and reality to the way that we observe that emergent level. So, there might be small differences. Maybe other organisms are more sensitive to sound or to smell or different parts of the electromagnetic spectrum, but the same basic clumps of reality that we call the higher emergent levels are going to be more or less universal. Gary Miller says, if medicine could someday prevent the body from developing tolerance to recreational drugs so that you could take a safe small dose, is there a drug or drugs that you would take, like alcohol, psilocybin, heroin, amphetamine? Would you take it daily if it were not at all harmful? I think the only thing I would take daily, other than caffeine, would be alcohol. I've long lamented the fact that I really enjoy the taste and aesthetic pleasures of good wine and cocktails and things like that. But there's a limit. Different people's body chemistries work differently. This is something that Jennifer wrote about in her book, Me, Myself, and Why, Searching for the Science of Self. Some people, once they have a little bit of alcohol, they need to have more and more. Others, once they have a little bit of alcohol, they want less and less. So she and I, for whatever reason, are both on the side that we can have a couple drinks and that's it. We actually don't want any more, right? Because the feeling isn't pleasurable anymore. And but the taste is still pleasurable, so I would love to be able to have as many martinis as I would like without feeling any effects at all. That would be great. I'm not in it for the intoxication for the most part. For the others, I think I would, not having tried them, I am curious about them intellectually. Like, I've always felt that in depictions, in books or movies or TV shows or whatever of being on drugs, that always seems horrible, right? Like, you're sort of disoriented, you don't know what the world is doing and everything. There's no indication in these depictions that this is something you would want to do again and again. But clearly, people do want to do it again and again. They get addicted to it. So there has to be some positive aspect of it. I don't like the idea that, you lose control of your faculties and so forth. So if that were part of it, I would have no interest whatsoever. But I am curious as to what the addiction feels like if you could actually not be addicted to it. That would be interesting. And the psychedelic drugs are, of course, a completely different thing than more addictive drugs. They give you different experiences and so forth, which I think are amusing and interesting, but I don't have any profound feelings about a need to try them. But again, for intellectual curiosity reasons, I would be very interested in giving it a shot. Jared Sage says, I have a thought experiment I'd like to pose for consideration. We discover a galactic community of alien Type 2 Kardashev civilizations, and we are invited to join them if we begin a transition into a Type 2 civilization. However, someone is able to prove that no human civilization of that size or complexity is sustainable without the systematic sacrifice of human individuals' selfhood, certain liberties and human rights, etc., for that civilization. It is certain that some, perhaps a lot, of that sacrifice will result in individual suffering. If we don't join them, we can reasonably be sure that we'll effectively be alone in the universe until our extinction. Are individuals morally obliged to leave behind ego and identity for the transcendence of the species? Or is the species morally obliged to sacrifice its own transcendence for the sake of the sentient creatures it comprises? I think I get the thought experiment, but I don't think it is well enough defined to actually give you a sensible answer. In other words, I don't think that there's any overarching answer to the question, are individuals in general morally obliged to leave behind ego and identity for the transcendence of the species, or vice versa? I don't know what it would be like to leave behind my ego identity for the transcendence of the species. I personally don't feel like that sounds very attractive and want to do it, but maybe it would be. I think the relevant podcast to listen to here is Lori Paul talking about transformative experiences. How do you make rational decisions based on trying to maximize your utility, let's say, or some utility function, if the experience that you're contemplating doing would radically change your utility function? It's not obvious what the answer to that is. I think you can make good cases for either, what you would do in maximizing your current utility function, which sounds like I would avoid being absorbed into the Borg collective, but maybe I could also make a case for maximizing what it would be like once I were there. I think it might depend on exactly the details of what that would involve. Are there memories that are kept? Is there great individual suffering involved? I think sometimes you have to look at the specifics, not just rely on general principles. Ruarid says, having recently given up my career in London to go back to university to study a physics undergraduate part-time at the age of 29, I'm now in my third year before I plan to apply for PhDs here in the UK. I finally feel like I'm pursuing my dream of becoming a scientist, albeit a decade behind my peer group. Despite everyone telling me I was making a mistake in leaving my career, I've never looked back. My primary goal is to get a PhD in physics or applied maths and see where it takes me, preferably into research. Do you have any words of wisdom or advice for me? I think that the time when any words of wisdom and advice would have been most useful have already been passed, because, of course, you've made the hard decision to actually go back and study physics, and you seem to be enjoying it, right? I think now the fact that you had a career and you're 29, so you're 10 years older than your peer group, doesn't matter that much, right? I think that of course, there are words of wisdom and advice to give, but they're more or less the same, whether you're 29 or 19 in this case. Learn all the physics you can, if your goal, again, is to become a researcher, a professor, or something equivalent to that. Learn all the physics, the applied math that you can learn. Do research yourself. Catch up on what is going on in the research fields that you care most about. Don't wait for the field to come to you. Read papers. Think about what is going on at the cutting edge. Think about what problems really capture your imagination and what areas you might have something to give back to. What is the intersection of your own interests and your abilities and the interests of the rest of the world? Talk to people, talk to professors. At some point you're going to need letters of recommendation. And I always feel heartbroken when I get a request for a letter of recommendation from someone who took a class from me 2 years ago and I barely spoke to and barely remember. You want letters of recommendation from people who know you well, from professors who know you well. That means make sure that there are some professors, 3 of them in particular, who know you well enough to write a good letter of recommendation. Be forward-thinking. Take the initiative. Think about where you want to be. Start trying to be there. If there's some subject that you need to know that your university doesn't teach, learn it yourself. Buy the book. Read it. Download some lecture notes from the internet, look at an online course, watch some videos or something like that. Act like you are a working researcher long before that is your actual job title, and I think you'll be fine. Congratulations on where you are already. Tom Arabia says, Andre Linde once said that the cosmic microwave background is like a photographic plate, a picture of the universe a billionth of a second after the Big Bang. For those of us with dreams of a final theory, it seems like we are compelled to hope that there is enough information in that picture to decode it. Because we can't build a collider big enough to probe the distance scales where gravity becomes important to scattering amplitudes, but the observable universe might be an adequate atlas detector for an experiment that did probe those energies 13.7 billion years ago. What is your prior probability that there exists enough information observable with any feasible telescope to nail quantum gravity? Well, my prior probability is extremely low for that one. Sorry about that. The thing about the universe as a particle accelerator is that it's a very crude one. It only did one experiment, and we didn't design the experiment. We didn't optimize it to give us the clearest possible results. So sadly, it is a feature of effective field theory and other aspects of how physics works across energy and timescales that often what happens at the scales where quantum gravity is important or other high energy physics is important, grand unification or whatever, just get all washed out by the time you get to the observable level. In particular, for the cosmic microwave background, we don't have that many observables, right? We have a very large number of modes of density fluctuations we can observe, but as far as we know, they're mostly described by a very simple statistical distribution. There's not actually a lot of very, very interesting information contained there other than that distribution, which is only a few data points, right? Nowhere near enough to pinpoint a theory of quantum gravity. So by all means, we should squeeze all the information out of the CMB that we can. But to expect it to nail down high energy physics, I don't think is super realistic. We can hope, we can try, we should hope and try, but to expect it, I think is a bit too much. Diana Newman says, a priority question. You have been an advocate for popularizing science and have done much to advance the cause, yet science is being degraded and discredited daily by culture wars, censorship, and self-censorship in academia and among other scientific authorities. Has Brandon Abunu defended fellow evolutionary biologist Carroll Hooven, who was forced to resign her position at Harvard because she taught that there were two biological sexes? Have you? And can we be honest that believing in vaccines isn't a binary question, as though the polio vaccine is comparable to years of COVID vaccine mandates for healthy young adults attending college? I have no idea whether Brandon has defended Carroll Hooven. I don't know who Carroll Hooven is. I haven't defended her myself. As a general principle, I have zero interest in demanding that some people condemn or support or defend other people in general. You know, I don't think that demanding that people make statements about things that are not directly related to them or their responsibility is a generally relevant thing to do. So I have no idea. Believing in vaccines, it's true. It's not a binary question. But in the real world, there's been enormous anti-scientific, misinformation-laden attacks against the efficacy of vaccines. And the thing I'm worried about is that people who don't take science seriously are being put in charge of our healthcare system right now. That worries me a lot more than debating this or that vaccine mandate. I think vaccine mandates are extremely non-harmful overall. Philip Brooklyn says, my question centers on how to handle evidence-based reasoning while supporting friends dealing with health concerns. A friend experienced headaches and tinnitus after a mobile, tinnitus, not tinnitus, tinnitus. After a mobile antenna was installed near his flat. I suspect this may be a nocebo effect, which is kind of like a placebo effect, except bad things happen to you. But I haven't checked the research or whether there's a plausible mechanism. In my view, my friend tends to be a hypochondriac, but he was convinced the antenna caused his symptoms and eventually moved out of a flat he loved. I didn't challenge his belief as I didn't want him to feel dismissed during a stressful time, especially since at one point he couldn't stay in the flat for more than 20 minutes without getting a headache. How can we handle situations where health concerns are tied to uncertain science while still supporting someone's experience in maintaining the relationship? Yeah, this is a very good question overall. I share your skepticism. I might even be more skeptical than you that having a mobile antenna near your flat could cause headaches and tinnitus. Maybe it could, but I don't see what the mechanism for that would be. I would like to see some really good empirical studies about it before I became convinced. But mostly this is not a science question, right? This is a human relations question. The general principle being, how do we deal with friends of ours who we think are just acting irrationally for some reason or another? We want to support them, especially if their irrational actions are leading them to suffer for some reason. We want to be supportive, but we also want them to be rational, and we don't think that they are. You don't need an antenna near your flat to make this happen. You could just be like dating the wrong person, right? And they could be dating the wrong person in an obviously irrational way. Maybe some of us have even done that ourselves and know what it's like. So I think that there's a human level answer, but it's not going to be a one size fits all answer. Yeah, I think that this is the theme of the AMA this month, is that sometimes the details matter, and sometimes there's no one size fits all answer here. You just have to do the best you can. How responsive, receptive is your friend to sitting down and thinking reasonably about the possible effects of an antenna? Like, are they interested in looking at scientific studies about this or looking into mechanisms, or are they completely closed-minded about this? I think that it matters. There's no reason to bang your head against trying to convince someone of some rational scientific result if they have zero interest in doing that. Sometimes you're just going to have to let them be irrational. And, that's kind of okay, right? There are worse things. Like, as long as they're still a good person and friends with you, they're in some sense causing suffering for themselves and in a way that you personally can't talk them out of, right? You might not be able to talk someone out of dating the wrong person either. Sometimes people just have to figure it out for themselves. Other times there is a little open window, right? Maybe, or a crack in the door, I should say. Maybe they're not completely devoted to that particular non-rational belief, and maybe you can find ways to say, to try to be supportive, to say, well, okay, maybe you're right. Let's sit down and do the research together. Let's go through the scientific studies. Let's think about it. And rather than lecturing them and hectoring them, you can go on a journey with them, and hopefully that journey leads them to some better place. Yazan al-Hajari says, I am an artist, a composer and filmmaker, with no formal scientific training, yet I found myself drawn to studying relativity purely for the joy of it and out of curiosity. As someone with a deep understanding of complex scientific concepts, what advice would you have for someone like me who's learning these ideas just for the sake of exploration? How should I approach studying such profound topics? And at what point, if any, should I stop and embrace the beauty of the journey rather than the application? Well, I think you should always embrace the beauty of the journey rather than the application. You might have an application, that's fine, but if it gets in the way of your embracing the beauty of the journey, that is bad, especially if this is not your job, right? If this is not, if you're trying to train to be a professional physicist or a professional anything else, composer and filmmaker, I am sure, parts of that job, parts of the training for that job are tedious, right? There are things you got to do. You got to do your calisthenics before you get to play in the game. You have to learn to symmetrize the Riemann tensor or whatever before you can solve Einstein's equation. There are parts of any worthwhile thing to do that aren't themselves totally worthwhile, but still have to be done. But if you're not doing it as your job, then you kind of have a little license to just do the fun part, to embrace the beauty, right? To learn the parts that fascinate you, that really resonate with you, that maybe will be relevant to your own work later, maybe not. But in the meantime, you're learning cool things. And that's really, really what's important. If you do want to learn at a deeper level, I think we all know what the big threshold here is. Do you want to learn the math, right, when it comes to things like relativity? I might mention that I've written a book, The Biggest Ideas Volume 1, that does some of the math behind relativity. You could at least look in a book like that and get an idea of whether the math is something that you would want to dig more deeply into. And if not, that's fine. You can just read all the books you can, listen to all the documentaries you can, and just enjoy it, right? The trick is attempts to popularize relativity and quantum mechanics, as you will learn, as you will get the impression of just from listening to this podcast and these AMAs, you can absolutely learn about things in that way, but it's hard to learn them so well that you can generalize them, right? It's hard to learn things at a sort of popular level so well that you can put yourself in the shoes of someone who does it professionally and extend the examples you've been told outside the domains of their original applicability. This is where people get in trouble with, analogies and things like that. So it's completely up to you. I would certainly not put pressure on yourself to learn more than you're comfortable with or is interesting to you. If the real thing is you're worried about getting it wrong in some, I don't know, film or composition or something, find someone who you can talk to, right? Find a local graduate student or someone like that. Go on Reddit or Quora, or I don't even know where to go. But there are places you can talk to people who know about physics quite a lot, ask questions, have a conversation, and learn about things that way. Or maybe just, on Blue Sky or whatever, some social media site might work also. But again, just don't, fret too much. It would be a shame if your desire to learn more physics became something that made you anxious rather than something that made you delighted. Brian Mendoza says, for your Christmas wish, I'd like to grant you the ability to modify anything about physics or quantum mechanics that you'd like. Are there any parameters you'd like to adjust? Or if you're pretty happy with the current configuration, that's fine too. It's a good question. I'm going to give the wimpy answer and say that probably I don't want to adjust anything. And the reason why is because who knows what the implications would be, what the consequences would be of adjusting something. I mean, we all know, I think it's pretty clear that small adjustments to, let's say, the constants of nature or the forces of nature, the field content or whatever, can have very dramatic consequences on the large-scale structure of things. If the neutron were lighter than the proton, the world would be an entirely different place. If the electron mass was very different, or the charge-to-mass ratio, different things were different, the world would be a very different place. If electrons were bosons, the world would be a very different place. It's, and on and on. So I would worry that not only would I not exist, but, no intelligent life would exist if I messed with the laws of physics just a little bit. I guess the one exception might be it would be fun just at a completely selfish and personal level if new physics were right around the corner, right? I could change the laws of physics, not in the regime we know, but in the regime we don't yet know, so that I would find a paper tomorrow from the Large Hadron Collider having discovered new particles, or, some new dramatic signal of gravitational waves or something like that in the microwave background. Who knows? But it would be certainly individually, selfishly fun if there was, if the next 50 years were full of these amazing science discoveries, and that could be plausibly come to life if we adjusted the parameters correctly. But I don't have any specific details. I don't care what they are, what those new physics results are. I just want them to be accessible to me, and that's entirely selfish. I'm sure that the laws of physics get along perfectly fine even without that. Tim Converse says, biochemists spend a lot of time figuring out how organisms prosper by exploiting energetically favorable chemical reactions. My question is about the extent to which organisms also exploit increasing the entropy of their environment. Is it in fact the case that the sum of what an organism consumes comes in a more ordered state than the sum of what it excretes? If so, is that difference in entropy key to the ability of an organism to survive and reproduce? I love this question because the answer is yes and yes, very, very straightforwardly. You've just sort of put exactly what organisms do. As Schrödinger said in his book, What is Life? A living being is something that continues moving long after you might have thought it would stop. And what he meant by that is living beings take free energy in from the environment, which is to say energy in a low entropy ordered form, and they use it. They put it to use. They put it to use in repairing themselves, right, in repairing their mechanisms, their DNA and whatever, and also in doing work, in moving from place to place, in hunting for even more free energy, because mostly it's about survival and reproduction, etc. Yes, all of that is entirely 100% dependent on sources of low entropy energy, which are then degraded and turned into higher entropy energy in the course of the life of an organism. Roman Schernbichler says, as a software developer, I find the similarities that we can find at different scales in our universe fascinating. That the brain and the cosmos show similar patterns is incredible. The idea that the universe could be a fractal is something that resonates with me. How do you feel about that? Yeah, I think that it is, on the one hand, fascinating and cool that there are similar patterns at very, very different scales of existence. On the other hand, don't push it too far. You don't want to draw too close of an analogy between the brain and the universe. The brain is a strongly interacting system, right? The neurons all talk to each other in a very, very intimate way. That is a hugely important part of what the brain is and how it works. The galaxies in the universe don't talk to each other for the most part. Galaxies in a certain cluster of galaxies will bump into each other, but they're big puffy clouds. They don't, pass information back and forth in any very ordered way like neurons do. And galaxies in different clusters just don't even bump into each other. They don't even really interact with each other. There is it a fractal, the universe? Well, I don't know. That depends on how you define fractal and how you coarse grain and all sorts of details like that. Certainly there is some scaling behavior in the universe. There are some features of the organization of the universe that obey power laws in space. But again, it's not the kind of structural organization that you have in a brain or in other complex systems. So I both think it's really interesting to have these similarities of patterns, but you want to actually understand why the patterns got there before you become too happy about the fact that there are those similarities there. Kevin's Disobedience says, why is pilot wave theory underrepresented or unrepresented among physicists? In my mind, the fact that it was independently derived and takes both the wave and the particle to be ontic structures should, I would think, increase one's credence. No? Well, I think that there's a bunch of reasons. There's two very simple reasons, and there's probably other tinier ones. The two very simple ones are most physicists don't see the need for it, okay? You got to say over and over again, most physicists don't think deeply about the measurement problem of quantum mechanics. They think it's fine to just say when you measure a system, its wave function collapses with a certain probability. The fact that the idea of measurement is not defined at the end of the day doesn't bother them. They just want to get on with their lives and make predictions, and that works fine. It's worked fine for 100 years. It fails when you want to get more careful and more deep, and maybe when you want to understand the emergence of space-time and things like that. But for most working physicists, it's fine, so they just don't worry about it. Why would you bother mucking up your theory with hidden variables if you have a theory that works fine? The other reason is that among the people who you might think would care more deeply about the foundations of quantum mechanics within the set of working physicists, they care about quantum field theory, right? And hidden variable theories don't play well with quantum field theory. They play very well with particle-based theories, but we know the world doesn't work like that. And I know that there are advocates of pilot wave theories that try very hard to reconcile quantum field theory with pilot waves, but honestly, their attempts are not that convincing, not that impressive. They have very basic questions that remain unanswered, whereas just looking at the wave function and doing the regular thing without any hidden variables, again, gets you the right answer right away. So I think there's not a lot of motivation, and there's a certain amount of anti-motivation. I'm glad that some people are working on it because maybe they will make breakthroughs, who knows? But most of us are just not that motivated to think about it. Keith says, in the solo episode on emergence, while outlining systems as having states and rules governing the evolutions of those states, you mentioned the choice for a Markovian restriction, where the present state holds all the information to predict the state in the next moment in time. You briefly alluded to the idea that this may not really be a restriction because we can always reformulate a space of states as Markovian by including past information in the present. Would you be up for elaborating on this a bit? It seems similar to a notion that even though fundamental physics laws are Markovian or memoryless, as some disciplines say, it is contained within the present things like hard drives and brains that clearly do remember past states, but that memory state is still governed by a Markovian rule or law. Yeah, I think that you've just elaborated on it very, very well. I think here's the intuition. If you think that the underlying laws of physics, the fundamental laws of physics, are Markovian in the sense that the current state, it's a Laplace's demon kind of situation, the current state plus the laws tell you exactly what will happen toward the future. In particular, you don't need to know the past, you only need to know the current state, okay? But then you coarse grain. So you go from the current state of all the molecules, et cetera, to some coarse-grained information, about like the location and the center of mass and the size of some macroscopic objects, okay? If you only kept the kind of similar information that you had at the microscopic level when you talked about the macroscopic level. So if I only kept for a person their position and velocity, right, or maybe the position and velocity of some of their appendages or something like that, that would clearly not be enough to predict what the person is going to do in the future, because the person has microscopic information contained in their brain that is going to affect what they do in the future. Okay, so you might think, well, it's not Markovian. A person, we all talk about the fact that people are affected by their past experiences, right? So we generally think about people as absolutely being affected by things that happened in the past in a purportedly non-Markovian way. But I just think that all of that is overly casual and not very thoughtful, right? Individual people are affected by the past only to the extent that the past has affected their present situation and their present state, if in the state we include things like their memories and predispositions that were shaped and molded by past experiences. Those are the things that matter. So I think that it's just a matter of having an effective, a correctly formulated higher level emergent theory, where people have memories as well as current mental states and things like that. Once you do that, everything is perfectly Markovian at this level. Now, I'm not saying that this is always the right thing to do. There might absolutely be cases where it's just more sensible to explicitly keep the past as a specification of what is going on. I'm not judging that. I'm just saying that I see no cases in which it would not be possible to include every relevant feature of the past in the present state. Indeed, maybe there's a theorem that has to be possible if you think that the emergent dynamics are fundamentally compatible with an underlying dynamics that truly is Markovian. Tariq says, my understanding is that the lifetime of a black hole is one of the longest, if not the longest, of any object. Is this due primarily to the amount of mass they contain or the relativistic effect on time from their density, which makes the rate of any process that would allow the black hole to decay so slow relative to everything else in the universe? Well, I think that the lifetimes of black holes are small just because black holes can grow very big. I think that's it. I think that's really the only reason. Coupled, of course, with the fact that the way that black holes eventually decay is through Hawking radiation, and Stephen Hawking's formula says that big black holes actually radiate more slowly, less energy, lower temperature than small black holes. So that's it. It's just that, they're very big and they decay very slowly, so they live a long time. It's nothing very profound. It's nothing to do with time dilation or anything like that. I don't necessarily think it's true that black holes are the longest lived objects in the universe. That will depend on details. It depends on details of things like proton decay. Are protons truly stable? A single hydrogen atom all by itself would live much longer than a black hole unless it's proton decayed, in which case then you don't know. If the proton decays in 10 to the 35 years, that would be a shorter lifetime than a supermassive black hole. But it's just a matter of detailed calculations. It's not a matter of some big overarching principle that says the black holes have to live longer. DMI says, how can democracy survive the next 4 years? Well, that's a hard question. I am sobered by the fact that it's a reasonable question to ask. I do think that democracy probably will survive the next 4 years. I presume one means democracy here in the United States, not the idea of democracy, which I'm sure will survive longer than 4 years. But when I say that democracy will survive effectively in the United States the next 4 years, probably, I don't mean probably like 99%. I mean like 70%. Which means that there's a 30% chance that it won't, which is huge. That's like a disastrously large, ugly probability to confront. And I think a lot of it will depend on people in the Republican Party who are not Donald Trump. Donald Trump is our president. He would be perfectly happy, as anyone who's paying any attention to the people who he is nominating for various cabinet positions and other federal offices will know. He's perfectly happy to replace the democratic system with a personal fiefdom of people who are loyal only to him, not to the American democratic system. But he's not the only one who has a say in the matter. Members of Congress, members of the Supreme Court, people who work for the executive branch in different capacities, they will also have a say in the matter. It is basically up to them over the next 4 years. How much will they let him get away with? it looks like, as I'm recording this, that all three branches of government, and including both branches of Congress, will be controlled by Republicans. So, as much as I wish that the Democrats could have an influence on it, they're not going to have that much influence. At the state level, they will. So, states can resist. And I think that resist in particular, I don't think they should just resist everything Donald Trump says, but they should resist things that are dangerous to democratic norms and traditions and institutions within their individual states. Hopefully they will do that. But there's a lot of states that are governed by Republicans also. So again, I think it's going to be up to the Republicans. How much does Congress and the Supreme Court let him get away with? And it's entirely possible that they will let him get away with a lot, but they will at some point rein in the authoritarian impulses that he has, and so much so that democracy can go forward 4 years from now. But it's also entirely possible they won't. That's why I think that it's a large credence on either possibility happening. What can one who is not a Republican official do about this? I do think that Republican officials, for what it's worth, care a little bit about popular opinion. So I think that convincing our fellow Americans that this is a bad thing to erode the foundations of democracy, even if it gives you short-term gains in your policy goals, is something to be taken very seriously. It's a tough sell. As far as I know, the data from people who do surveys and things like that tell us that supporting democracy is just not a very high goal among the American populace as a whole. That's another reason why the probability of disaster is so high, that it's not like 90% of Americans are absolutely devoted to this, because, again, being devoted to democracy means being willing to concede results of elections when you lose them. And that principle is just not very popular these days. So I guess we can continue to try to make that point as widely as we can. But if you're not, a member of Congress or the Supreme Court or some local official, then there's not a lot of direct influence that you have other than indirectly through the populace that they care about. Anonymous says, out of all the classes physics majors have to take, it isn't uncommon for physics students to say that their experience with statistical mechanics and thermodynamics wasn't great compared to other core classes. Why do you think physics students struggle with this topic compared to other core classes? Is it the book or the way that it's taught? Did you have a similar experience with stat mech and thermo? I think that's an interesting question. You might be right. I don't know if that's a horrible overgeneralization or not. I would be interested to see some data there. I don't think that stat mech tends to be taught very well. Statistical mechanics and thermodynamics are slightly different topics, right? Like when I was an undergraduate, we had a second-year thermodynamics class and a third or fourth year statistical mechanics class. Thermodynamics, both classes should be fascinating, right? They should be super duper interesting. Part of the problem might be that the people teaching them know a lot about the applications, but not a lot about the foundations. So, you're zipping right into some application, and maybe the students don't care about that particular application, right? Maybe they do, maybe they don't. Some of the and that might be just as true for classes in relativity or quantum field theory or whatever, or electromagnetism or what have you. Another issue is that a lot of the things that are true in thermodynamics and statistical mechanics are actually way deeper than we give them credit for. So in particular in thermodynamics, if any of you have taken thermodynamics as an undergraduate, you will have a vague recollection of things like Maxwell relations. These are different than Maxwell's equations. But there's this feature in thermodynamics when you have a box of gas. You can talk about the volume and the pressure and the density and the number of particles and many, many different things, and they're kind of redundant, right? If you know the total volume and the density, you know the total mass. But you can treat all of these different things independently. And so there's choices to be made about what are your independent variables, right? What are the variables you are allowing to change, and what are the ones that you're keeping constant? And this seems very puzzling, and it seems very arbitrary. Like you have to memorize a bunch of facts about, oh, if I change this while keeping that constant, that's related to changing this other thing while keeping that constant. And it's all kind of mysterious. It turns out that this is all differential geometry. This is all treating the space of states as a manifold with different coordinates, and you're just changing coordinate systems in a way that differential geometry makes perfectly clear. But no one, when they're a sophomore in college learning thermodynamics, knows any differential geometry or even is that comfortable with partial derivatives, okay? So you end up learning these ideas that are actually very profound in ways that seem like kind of arbitrary and kind of memorization based. Likewise, once you get to statistical mechanics, there's all sorts of profound things about different kinds of statistics and the past hypothesis of entropy growth and things like that. But we kind of gloss over a lot of that to get to some, formulas for the Maxwell-Boltzmann distribution, the Fermi-Dirac distribution, or whatever, and then some calculations to do. At the end of the day, physics professors like teaching you things about which they can then assign problem sets, as we were talking about before. And so a lot of the beauty and depth of these subjects is lost by that approach. I have no idea how to fix any of these problems, but I do think that it's a shame that the intrinsic beauty of stat mech and thermodynamics is not always conveyed by undergraduate educations. Derek Corwin says, after listening to your solo podcast on emergence, I was wondering if there is a difference between emergence and emergent properties. E.g., temperature, pressure, and entropy are often cited as examples of emergence, but so are tables, with the latter labeled as emergent properties when I ask Google whether temperature is emergent. Meanwhile, we usually refer to a table, intuitively an object, instead of tableness, a property, e.g. a set of wood 2x4s. Since there are formulas for temperature, pressure, and entropy, but none for tableness, is this difference tied to the type 1a versus type 1b emergence, direct versus incompressible distinction that you and Atooth Parola laid out in your recent paper, or is there something else driving the difference? I think this is a good question. The discussion about emergent properties is the most common way that philosophers talk about emergence. Indeed, if you go to the Stanford Encyclopedia of Philosophy, which is a great resource for these kinds of things, they don't have an entry on emergence. They do have an entry on emergent properties. So it's clear that the assumption is that the thing that emerges are properties. But this is part of why Atooth and I said that we take a physics-inspired approach in our paper, or really a dynamical systems inspired approach. Because what we take emergence to be is about a relationship between theories at the micro level and theories at the macro level. And theories have objects in them and they have dynamical laws, but you can talk about properties at either level, right? You can talk about the property of being electrically charged. If you ask a mathematician or a logician, what is a property? A property is a subset. That's what it is. So what you mean mathematically by the property of having an electric charge -1 is you consider the set of all particles, and there is a certain subset of them, the ones that you and I say have electric charge -1. And that subset is the property, okay? This might not be the most useful definition from putting it to work, because what if we make another particle? How do we know what property it has? But in principle, that's what it means. And so whenever you have these higher level descriptions, you can always talk about properties. Properties are always there in our way of talking about it, but they're not the fundamental thing. They're not the central object of interest. It's the coarse-grained maps and the associated dynamics of those macrostates that are the interesting things. So when it's useful to talk about properties or not, well, I think it's always useful. Tableness is a property, but tables are objects. Electric charge is a property, electrons are objects. I think that whole distinction between properties and objects is just there at every level. And what we're sort of doing is shifting the focus from properties to objects and their dynamics. Richard Riley says, do you support nuclear power? I do because greenhouse gases from fossil fuels are by far the main contributor to global warming, and nuclear power generates almost none. Seems to me nuclear has to be part of the energy picture. Renewables can't make up for fossil fuels in the foreseeable future. The Sierra Club strongly opposes nuclear power, which to my mind makes their global warming advocacy pretty hypocritical. Well, I do support nuclear power, but I'm not pretending to be an expert on the trade-offs. I don't think that hypocritical is the right way to describe the Sierra Club. Maybe you just disagree with them. That's okay. I think that it's weird to me that these debates about nuclear and fusion and solar and fossil fuels become very emotionally packed very, very quickly, right? And you can just disagree with people. Just say, I think your analysis is off base. Once you start saying that they're hypocritical, then you're sort of making it a more fraught discussion to have, and you're gonna have trouble convincing people to change their minds. Look, nuclear power has pluses and minuses. It is the safety of it can be debated one way or another. By some measures, it's very safe. The number of deaths due to nuclear power is relatively low. At Chernobyl, there were absolutely deaths. But if you compare it to the number of deaths due to fossil fuels, one way or the other, it's no comparison. There's many, many more deaths because of that. On the other hand, there is the possibility of absolutely large calamities with nuclear power, which is harder to imagine with fossil fuels in exactly the same way. And of course, there's the problems with dealing with nuclear wastes and things like that. So there are actual trade-offs, and you actually have to think them through. Maybe after having thought them through, you decide that, yeah, nuclear power is absolutely worth it. It's the way to go. I don't actually necessarily agree that renewables can't make up for fossil fuels in the foreseeable future. Renewables are doing great. The rate of change of improvement in renewables is very, very good. But at the end of the day, I don't care. I don't care whether it's nuclear or renewables or whatever. I just want to do better than belching greenhouse gases into the atmosphere. Okay, so if it turns out to be nuclear, that's great. If it turns out to be solar and wind, that's also great. Whatever the actual experts decide is fine with me. Alexei Kostibas says, I really appreciate you helping elucidate ideas about emergence. Since I was a kid, I found it fascinating that bits of ones and zeros could turn into an experience like Doom, the game. Oh, not the existential threat of Doom, or that individual atom movements turned into temperature. There is something immensely fascinating about how things transition from binary to analog, sometimes over and over again as you change scales of perception. You don't seem to use the binary analog framing, and I'm curious if those words just aren't as useful as other ones. If they are, I'm curious if you can talk about the A to D conversion boundaries. For example, how many atoms does it take to have a temperature? Another. In organizational structure, a lot of folks use Dunbar's number and related ideas to indicate how when management priorities should change. Dunbar's number, if I'm remembering it correctly, is that number like of the most people that you can have in an organization or the most friends you can have or something like that. Some human level thing that I don't need to pay attention to. Anyway, I think that there's a lot going on here. The difference between continuous and discrete descriptions, which is the way that I would talk about it rather than analog to digital, but that's okay. It's the same kind of thing, is very, very important, but it's very subtle. If I have a set of ones and zeros in a lattice, that is absolutely a digital reality underlying things, but I can still approximate it by a continuum if the lattice spacing is very, very small, and I'm looking at many, many lattice sites all at once, okay? So it's an interesting situation. I think we've talked about this on the AMA before, but in principle, the continuum description has an infinite number of parameters because you have, density or whatever as a function of spatial location, and there's an infinite number of spatial locations. How can it be that that kind of infinite number description is somehow more compact than the finite number description that you have in the actual lattice? And the answer, of course, is that you don't have infinite precision in your continuum description. Maybe you have an approximate description that coarse grains regions of space into little cubes or something like that, and you end up having an actual finite number of variables to keep track of. So it's possible to go either way. It's possible to start with an underlying continuum and have digital descriptions, like you do it in hydrogen atom. The wave function is smooth, but as long as you're looking at energy eigenstates, especially low-lying ones, there's only a finite number of ones that matter. And likewise, you can have continuum descriptions arising out of underlying digital things. So I don't think it's that, I want to say it's not that profound, but it's not that profound all by itself. It depends on the situation. It depends on what is going on. There's all sorts of fascinating ways that you can have different ontologies at an emergent level than you do at a more fundamental level. I guess that's the fundamental thing to say. That feature of emergence is absolutely fascinating and central and worth looking at. I don't think there's a special property of continuum versus discrete, but it's part of the big property of just different ontological descriptions at different levels. In terms of when those crossovers happen, again, that's a very context-specific, situation-dependent question, and ultimately they will be approximate, right? There's not going to be one hard and fast number like here's a number past which – that's why I'm kind of skeptical about the Dunbar's number kind of descriptions. If you're less than this number, then you know everybody. If it's greater than that, you don't. Yeah, I think that's a little bit oversimplifying a messy reality. Nikola Ivanov says, you gave as an example of type 2 emergence a document like the U.S. Constitution. Could you please clarify how this can be social construct derived – how can this social construct be derived as an emergent phenomenon from the basic microlaws of physics, or how can it be derived from the filter function you proposed? Are you saying that there is a map between a specific configuration of neuronal connections in the brains of people familiar with it, or the atoms in the medium in which the Constitution is expressed and the concepts that it represents? Moreover, are you saying that, for example, the structure of the U.S. government can be traced back to specific neuronal connections in the brains of the Founding Fathers? Well, in principle, yes, but you see where you've gone off the rails from my perspective already because you're using the word derived right there in the beginning of your question. If you read our paper, what we say very explicitly, we're trying to undo use of words like derived in descriptions of emergence. There is a higher level theory. There is a lower level theory. If you had the explicit map from global states in the lower level theory to states in the higher level theory, you would be able to show which ones led to which concepts, but you never do in practice, not when you're talking about atoms to people in the United States obeying the laws, okay? You never have that explicit map. So the whole point of that example was when you're talking about the behavior of human beings here in the United States, in law courts or in legislatures or whatever, the concept of the U.S. Constitution is a very useful one. It is one of the concepts that you had better include in your emergent description if you want to have the most compact, powerful, predictive theory. Because people can say things like, well, I need to read this person his rights because the Fifth Amendment to the U.S. Constitution gives them these rights. I cannot, break up this assembly because the First Amendment says you have a right to assemble. Things like that, right? You invoke the Constitution in your explanations for why things happen at that higher level. But nobody thinks it's magic, right? Nobody thinks that there is an essence of constitutionality that floats in and becomes important only in certain circumstances. So it's not type 3 emergence. It's not augmented emergence or strong emergence. It's just that there is this higher level emergent quantity, which in principle is an equivalence class or a subset, if you like, of all possible microscopic configurations of everybody in the United States, indeed everyone in the world, to the extent that they interact with the United States, that we call the Constitution. But the whole point of type 2 emergence is that it's the non-local kind of emergence. So it's not that there is a location for the Constitution, right? It doesn't have a physical instantiation in the higher level world. It's an idea that sort of floats globally throughout the world. And the map, there is in principle a map from all the possible configurations of atoms in the world to configurations of the macrostate, including the idea of the Constitution. And in some configurations of those atoms, there is nothing called the Constitution. And in other ones, there is, okay? We have no idea what this is. We don't care what this is, what these maps are. That's Philip Anderson's point about more is different. You don't need to know the underlying micro theory to make sense of the macro theory, but you also, as Anderson would insist, don't need to pretend that the macro theory is incompatible with the micro theory. Ultimately, those connections do exist, even if you don't know what they are. Edward Crump says, what prevents another Big Bang from occurring? The honest answer is we have no idea. We don't have no idea why our Big Bang occurred, or even if there is an answer to the question why it occurred. People have talked about the possibility of new Big Bangs occurring, but there's different ways that it could occur. Therefore, there's no one right answer to this question. One way it could occur is that the universe collapses and bounces, okay? And then the aftermath of the bounce would be thought of as a Big Bang from the perspective of the people in that aftermath. Another way is you could pinch off a little baby universe from our current universe or the future of our universe. That's something that Jennifer Chen and I talked about, using ideas from Eddie Fari and Alan Guth and others of spontaneous creation of baby universes. And that's just unlikely. There's nothing preventing it. It's just that even if it could happen, the probability per unit meter, per unit year is very, 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 very small. In order for it to happen, you're just relying on the universe being very, 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 very big, so eventually it was going to happen. So I don't think anything prevents another Big Bang from happening. It just seems to be pretty rare. Bob Ritchie says, a modest proposal to change basketball using some rules from ice hockey. No free throws. If you commit a foul, you go immediately to the midcourt penalty bench. The other team gets the ball and your team plays shorthanded. It should be almost nonstop action. What do you think? Yeah, I think this is not a good idea for basketball. I mean, I'm not convinced it's a bad idea. This is the kind of thing that you might want to try out. Basketball is actually pretty good as a professional sport at tinkering with its rules to try to make the game better. And sometimes they succeed, sometimes they fail. But what you want to do is try in the minor league level or something like that, for something for fun, some fun tournament or something like that. But my strong prediction is that it would not work at all, for the basic reason that there are fewer people on the court in a basketball game than in a hockey game, and the scoring is much more frequent in a basketball game than a hockey game. So the advantage you have playing 5-on-4, if you're a competent professional basketball team, is enormously big. You can easily get somebody open, especially in this day and age where people are pretty good at shooting three-pointers. You would have a very, very big advantage from playing one more person than the other team has. I think it would be too big of an advantage compared to the current system where if you commit a foul, you just get to shoot a couple of free throws. So it's very hard to exactly calibrate the level of reward that the other team should get when you do something bad like committing a foul. I think that's an interesting place to look for ways to improve the game. I just think that having a penalty box is a bit too dramatic. I mean, Daryl Morey, who was on the podcast before and is president of the Philadelphia 76ers, would readily say that right now it's too easy in the NBA to shoot three-pointers. The three-point line is too close compared to the skill set of the people in the game. Yeah, I think here's a suggestion. What if we got rid of the three-point line? What if we just didn't have one, right? What if we went back to just having two-pointers? Because I think that the skill sets change over time, and people now are really, really good at shooting three-pointers. So it's very, very well known that the worst shot in basketball is a long two-pointer. that if you're just inside the line, it's not that much easier to make a shot just inside the three-point line compared to just outside, but you get only 2/3 of the set of the points for making that shot. So there's a huge disincentive to shooting from that distance. And there's something to be said for the joy of finding the best possible distance to shoot from. And maybe we're artificially altering that or distorting that by putting the three-point line in there. And of course, it's still, the best shot is still a dunk. That's still the highest percentage shot, most points per shot that you're going to get, even more than a three-pointer. But back in my day, when I grew up, the three-point line was there, but there weren't that many people who shot more than 33%, right? Who averaged 1 point per three-pointer. Now there's plenty of people who shoot better than 40% on three-pointers. So it's become just a really, really good shot, maybe too much so. So I can imagine tweaking the rules to changing that a little bit. I'm not quite sure how best to do it. Elias says, you've been known to state that the laws underlying the physics of everyday life are completely understood. What is your credence in this claim? What are the most plausible ways it could be wrong? Yes, I have stated that. If you're actually interested, I would recommend looking up my paper. The relevant paper where I lay out the case as explicitly as I can is called The Quantum Field Theory on Which the Everyday World Supervenes. And there I explain exactly why the credence is there and also what the plausible ways it could be wrong could be. I think my credence is very, very high, certainly over 90%, that something like that is true. And I list the ways it could be wrong. The most obvious way it could be wrong is if there's something weird about the collapse of the wave function in quantum mechanics. You know, part of the laws of physics underlying everyday life is the Born rule, that when you have a decoherence event or an observation event, the probabilistic outcome is truly random given by the Born rule statistics, right? The probability of seeing something is the wave function squared. And there's been all sorts of attempts to make that not true, right? Roger Penrose thinks that's not true, and he thinks it helps give rise to consciousness. So people like David Chalmers and Kelvin McQueen have actually dug into that. How can you change the Born rule in such a way that maybe it's relevant to consciousness or something like that? Doesn't really work. It's not really very promising if you actually sit down and think beyond like the sort of dorm room bullshitting level of analysis and actually try to get it right. It doesn't seem to work very well, but who knows? Maybe the right person just hasn't thought of the clever way to do it. So that's one way it could be wrong. Another way it could be wrong is if in some very fundamental way quantum field theory isn't right. In particular, locality and Lorentz invariance are both assumptions of quantum field theory. So if there were some violations of locality or Lorentz invariance, then that would mean that the laws are not quite right. Now, again, in the everyday life regime, we have super duper strong empirical evidence that locality and Lorentz invariance are fine. But we haven't looked at every possible way they could fail, so maybe they fail in some dramatic way. This would be essentially what would go on in the strong emergence case that we, as Achuth and I specified it in our emergence paper. If you imagine that electrons behave differently in the context of a human brain than in the context of a cantaloupe or whatever, I think once I looked up that a cantaloupe is on average the same mass as a human brain. That's why I like to use that example. But the core theory says that the behavior of electrons depends on exactly what is going on at the location of the electron and nowhere else. It does not care whether it's in a cantaloupe or a human brain. It only cares on what the electric fields and other things are where it is. So to go beyond that, to say electrons behave differently in the human brain than in a cantaloupe, requires a dramatic violation of the core theory. Could be zero evidence for it, zero sensible mechanism by which it could happen, but you never know. Anything is possible. Schleier says, you've said that you don't think the many worlds interpretation has an effect on ethical decisions. This is a comforting conclusion because it avoids an ethical quandary. Hypothetically, do you think your belief in many worlds is strong enough that you would do something that is ethical if it is true, but unethical if it is false? I don't know whether it's comforting or not. I think that the many worlds would not be of interest if it didn't fit the data, right? So by fitting the data, we mean if you believe all the claims of many worlds advocates, you predict quantum probabilities based on the Born rule, okay? The only extra difference is that all the probabilities actually happen somewhere, but they happen with different weights. So that's why they're attached different probabilities. So the claim that the many worlds interpretation doesn't have any effect on ethical decisions is just the claim that having many, many things happen, but with frequencies that are proportional to the Born rule, has the same ethical implications as only one thing happens, but with a true chancy propensity given by the Born rule. It's just hard to imagine, not impossible, but it's hard to imagine how that should have a difference. My belief in many worlds is, at the 95% level. So how is that strong enough that I would do something that's ethical if it's true, but unethical if it is false? That would depend on a lot. It would depend on how ethical, how unethical it is, right? If there's something that says that, act X would be if many worlds is true, would cause 1 billion times as much harm. Oh, is that right? Yeah, if many worlds is false, would cause 1 billion times as much harm as it would if many worlds were true, then maybe I would not do it, okay? But if it's just a little bit more harm, then certainly my belief in many worlds is good enough that I would, continue to do the ethical thing. It's not like I secretly don't believe many worlds, and therefore, gun to head, I would start acting differently because I've just been pretending this whole time. I think that many worlds is the most likely thing to be true, and therefore I'm going to continue to act as whatever the right way to act is given that belief until someone convinces me that some different version of quantum mechanics is more likely to be the right one. Redmond says, politicians flatter us that history is an arc bending toward justice. As a scientist, I assume that you reject the notion that history has any goal or purpose as veiled Christian millenarianism. As a philosopher, I further assume you reject this Hegelian nonsense as dangerous as it can be used to justify all sorts of mischief, as we saw in the Soviet Union and Gulf War II. Am I correct? Well, it wasn't a politician who said that history is an arc bending towards justice. It was Martin Luther King Jr. Maybe he counts as a politician in some way, but that's where the quote comes from. And it's more like I don't think it's supposed to be some sort of rigorous statement. I suppose it's supposed to be, we go back up to the question of hope versus delusion. It's a statement of hope. We like to think that things go better over time because human beings are trying to make them better over time. There are certainly ups and downs. I once tried to make a joke. No one got it. No one gets my best jokes. But back in the days of Twitter, I made a joke about the arc of the universe bending towards justice, and I put a plot up of a few random walks. Random walks with a slight positive bias, right? So there's like a 51% chance of going up, a 49% chance of going down. Run the random walk, and on average, you're going to go up. But guess what? There's a lot of times when you go down for a while until eventually you turn up again. That's more like what the arc of history is like, okay? Maybe even if in general there's a general positive tendency, which is arguable but is plausible, there's certainly a lot of ups and downs along the ways. I don't think you should make many of these assumptions about what scientists as a whole believe or what philosophers as a whole believe. You certainly can't say that as philosophers will generally reject Hegelian nonsense. There's plenty of philosophers who are pro-Hegel, okay? Just as an empirical fact. There are some scientists, not that many, who would say that history has any goal or purpose. But the idea that history has a goal or purpose is certainly not strictly limited to Christian millenarianism. There's plenty of other versions of the idea that history has a goal that are absolutely not Christian, right? I mean, Marxist versions of history are explicitly atheist, but can be absolutely thought of as teleological. So I tend to reject both of these. I don't think that even if the world overall improves with time as a tendency, that is some teleological statement. I think it's a statement about the hard work of people here in the world trying to make the world a better place. So I think you can believe it without thinking that it is Hegelian nonsense. But of course, you should also believe the limitations of this point of view and the caveats. Harold Cox says, priority question, why doesn't your wife have your last name? Did you take hers? I guess there's two answers. One is we both had careers before we met, and so we had published things under our names, so it's enormously more convenient just to keep your name, and we did, which most academics do, or most writers do for that matter. No, I did not take hers. The other reason is that, lots of people aren't doing that. That's kind of an antiquated thing. I don't think that taking your spouse's last name was ever an especially great idea, so I'm happy to be free of that. Nicken says, any tips in terms of building a personality or taking actions other than being studious and smart to make oneself open to collaboration in physics and to be successful in the long term? It's a hard question to ask just because it's very broad, right? Very, very vague. Building a personality is a sort of a complicated, many-faceted thing. I think this is not that different from a question we had months ago about dating advice, how to make yourself, compelling to the member of whichever preference you wanted to be attracted to you. It's not that different from how to make yourself compelling to potential physics or scientific collaborators, which is mostly stop thinking about that goal. Stop thinking about the goal of I want to be successful in the long term, or I want to have this person as my romantic partner. Start working on yourself, right? Start thinking about what science is interesting. How do we make the most progress on these science questions? What kind of person would I like to collaborate with? Certainly not one who either lectured me all the time and didn't listen, or was a milquetoast who only did what I said and never gave me any independent ideas, right? Collaboration, much like a romantic relationship, is a give and take. You have to be truly open. You have to be truly listening to the other person, not just because you want to appear like a good listener, but because you are actually interested in what they have to say. And you also have to offer something. You also have to give some good ideas. Do you have good ideas? Are you open to your ideas being wrong? Are you open to rethinking your ideas when you learn new things? Are you generous as a partner? Wow, it really is a very good analogy now that I'm thinking about it. Are you someone else wants to have as a collaborator? And I think that you can be plenty successful in physics without much collaboration. There are absolutely cases where people just are geniuses working by themselves. But in many ways, it's much more both productive and rewarding to be able to collaborate with people successfully. And I do think that the secret to that is just think about how to be a good physicist and how to do physics well, rather than how do I get this person to collaborate with me. Ralph Reich says, do black holes have a North Pole? I can imagine that they do, but how does it work if they are spinning very quickly? Do you think that the singularity itself has a magnetic north? Spinning black holes have a North Pole. They have an axis, right, around which they spin. If you're not a spinning black hole, then you're perfectly spherically symmetric and there is no North Pole or South Pole. Every point on the event horizon is created equal. In the real world, astrophysical black holes, we think, are almost always spinning quite rapidly. It's literally the conservation of angular momentum, like the ice skater effect. When the ice skaters doing a twirl pull in their arms, they spin faster and faster. Likewise, when a black hole shrinks and it accretes all this matter with angular momentum, it ends up spinning faster and faster. So most black holes are spinning. They have a North Pole and a South Pole. They can also have magnetic fields around them, but that depends on astrophysical details. But even without the magnetic North Pole, there will be two different poles, two different ends of the axis around which the black hole is spinning. Jeff B. says, do pointer states need to be put into physics as brute facts, or can they be derived? In other words, is the fact that we can measure a particle as spin up just the way it is, or can this fact be derived from an underlying theory? So I need to distinguish a possible confusion here. There are pointer states, which are kind of big macroscopic things. And then there are the observational outcomes of little microscopic things like spin that you're measuring. So the relationship is when you take a spin and you measure it, is it spin up or spin down? First, you measure it, which means that you do some physical manipulations to it that separate out the part of it which you would call spin up and the part of it you would call spin down, and then you entangle those with the rest of the world. The fact that with respect to some axis you choose, the x-axis, the y-axis, etc., you only get spin up or spin down, that fact is 100% derivable from the underlying theory, okay? That is a feature of quantum mechanics and how things couple to each other, that when you make that measurement, read up on, if you want, the Stern-Gerlach experiment, which does exactly this, measures the spins of particles. Why do particles only go up or go down? In some way, in some very vague sense that is incomplete but maybe helpful, it's because no matter what the spin is, it can be considered as a superposition of spin up and spin down. And by building the experiment in a certain way, you are choosing to couple to that particular aspect of the particle, and therefore you are separating out the part of the particle that is spin up from the part that is spin down. But none of that is a pointer state. That's just an observational outcome for this microscopic particle. The idea of a pointer state is when we magnify that measurement outcome to be read out by a macroscopic device, like we imagine something with a dial that has a pointer on it. And there's an entirely different discourse that comes in, because you need to take into account what kinds of macroscopic quantum states are robust against being monitored by their environment. And the result, roughly speaking, is states that are coherent in terms of their spatial configuration, right? Things that have definite positions and orientations in space are the things that are going to be pointer states. The cat is awake, that's a pointer state. The cat is asleep, that's a pointer state. The cat is 1 over square root of 2 times awake plus asleep. That is not a pointer state. And there's a long discussion involving decoherence and locality and so forth about why pointer states are pointer states, and also about why they're relevant, and that involves being out of equilibrium and entropy increasing and a whole bunch of other things. So there's two different sets of questions. The first set about why we only get up and down rather than something else is actually easier to answer. The latter question about pointer states is more complicated, but we think we have the basic ideas understood. Astro Nobel says, we assume that the universe is globally flat, but locally there's positive curvature associated with mass concentrations like clusters of galaxies. As I understand, this is compensated by voids where the curvature is negative. However, in the voids there is still a certain amount of mass, albeit much less dense than in clusters. How can a positive amount of mass be associated with a negative curvature? So first, I don't think we assume the universe is globally flat. When I was your age, we certainly didn't. We imagined the universe could be positively curved, negatively curved, flat. The experiments are telling us that it is very, very close to globally flat. So that is what we then go with and we move forward. But it's an empirical finding, not an assumption. The other thing is that, roughly speaking, this is the answer to why there's negative curvature in the voids is, from a strict general relativity point of view, not even a good question, because curvature is a more complicated thing than positive or negative. That's the whole reason why you need a Riemann tensor with 4 indices on it to actually talk about what kind of curvature there is in space-time. The reason why we're able to talk about curvature as either positive or negative or zero when you talk about the universe as a whole is because we're making vastly simplifying assumptions that the universe is homogeneous and isotropic. When the universe is homogeneous and isotropic, you've eliminated so many possibilities that you're left with just one number. Is the curvature positive, negative, or zero? Whereas if you're not completely homogeneous and isotropic, such as when you have voids and galaxies and things like that, curvatures are much more complicated than that. It's a more subtle issue than just positive or negative. There's a lot of components to the Riemann tensor. Okay, but with that in mind, I take the spirit of your question, and this short answer is the universe is expanding, right? It's not just that there is some matter in the voids. There is some matter in the voids, but there's also an overall expansion to the universe. So if you think about the universe in the perfectly smooth approximation, okay, the curvature of space can be thought of as a balance between the expansion rate and the mass density. And the expansion rate and the mass density have to completely cancel each other out, so you have zero curvature. If there is more mass density, you have positive curvature. If there's less mass density, you have negative curvature. And that same thing, roughly speaking, because of all these previous caveats, applies to galaxies versus voids. To the extent that you can call a galaxy or a cluster positive curvature, in the expanding universe, the voids are negative curvature because they're compensating for the positive curvature in the galaxies and the clusters, and they do so because the universe is expanding. That counts as a negative amount of curvature. Anthony Rubo says, do you believe there is a layer from which all emergence emerges, or is it emergence all the way down? I do think that there's a bottom layer, yeah. We don't know for sure, therefore this is entirely a guess. But on the one hand, I think it's conceptually simpler to imagine that there just is a bottom layer, even if we don't know what it is. And I literally cannot imagine what it would be like to have emergence all the way down. Maybe, it's one of those things that is an easy sentence to say. I think it's emergence all the way down, turtles all the way down, layers of the onion forever. It's very hard to turn into a working, rigorous theory. And I see no need for it. So I don't put a lot of credence on that. But it's absolutely not something that I'm confident in. It's not something we have any right to be very confident in. So I'm open either way. Final question for this month's AMA comes from Christopher Matthews, who says, this is going to sound like I'm using flattery to get my question answered, but so be it. I've never said that flattery doesn't get your questions answered. I just want to put that hint out there. I was watching your recent Royal Institute lecture and reminded how funny and comfortable you are in front of an audience, particularly during the Q&A session. Is that a talent you've always had, or is it something you've had to work on? So thank you, Christopher, for the kind, flattering words. To the extent that it's true, I try to be funny and comfortable. I try to make the audience comfortable. The stuff I talk about is often non-intuitive and a little brain stretchy. So, you want to lower the tension. You want to, release the tension with a laugh now and then. And you want to come across yourself as comfortable rather than tense, because this makes the audience more interested in the actual substance of what you're saying. To the extent that I succeed, it is certainly not a talent that I've always had. It is 100% something I've had to work on. I've told the story many times, so many of you here have heard it before, but I was on the speech team in high school, and I was terrible at feeling comfortable. I was very awkward, very stilted. My delivery, as they say in those contexts, it was very bad. And I just worked at it, and it's working at it in a mixture of, here's this thing I can clearly do better, plus things going on beneath the surface that you're not consciously aware of, right? You just do it enough that you don't become nervous. Like I gave a talk last week and someone asked beforehand whether I was nervous. And, no, I'm very honestly not nervous most of the time giving talks. There are certain contexts in which I might be, but I've just given a whole bunch of talks. There's no better way to become comfortable and at ease with it than to really feel like you know what you're doing, that you've done it before, that you're well prepared. Preparing well ahead of time is very helpful. Making sure that the stuff you're talking about is material you're very comfortable with. And the act of giving a talk is something you're very comfortable with. And there's no other way to do that than by doing it over and over and over again. And you will get better and you will get more comfortable. Not everyone gets better and more comfortable at the same rate, but caring about it, trying to get better, trying to solicit feedback, what worked about my talk, what didn't work, how can I be better, and being open to taking that feedback into consideration and working at being better can make you better at it. So if this is something that you're going to try to do, for better or for worse, it is something that is not necessarily a natural gift. It's something that you can absolutely become better at by working on. Maybe someday you'll have your own podcast. Who knows? Anyway, thank you, Christopher. Thank you, everyone, for asking questions, for listening along with this month's AMA. No AMA next week, so I'll be talking to you in other episodes, of course, but the next AMA will be end of January, beginning of February. So happy holidays, Merry Christmas, Happy Hanukkah, Happy Kwanzaa, Happy New Year, Happy... what is it called? What do the ancient Greeks call it? Saturnalia? Does anyone out there still do that? Whatever it is, whatever your particular winter solstice celebration is, enjoy that, and I'll talk to you again soon. Thanks.